Okay, so once again, good morning, everyone. Yeah. So basically, like I know yesterday we said we are going to start with evaluation form, right? But then, after much thought, we are going to actually be starting with the coefficient form, right? You guys are going to walk me through. This is the example we did yesterday, right? You guys will walk me through the process. It should be fast, right? And after we are done, then we are going to look at the evaluation form. So the evaluation form is not so straightforward because you're going to be doing division, right? You're going to be dividing a polynomial, a multilinear polynomial in evaluation form. What does that even mean, right? Does everybody have any idea what it means? Small? Okay.
So you find both to divide in evaluation form, you find both the quotients and the numerator separately.
Yeah.
I think you find where let's say we're looking for in this one, this first one,
Yeah.
to find the quotients, we look for the points where a is 0 and a is 1. Then we have divide it at that point.
Then we divide it at that point.
Like just like we did previous that we were taking half to split that
Okay.
point.
Okay.
Yeah, I think we do something similar to find where A exists and where A exists. That kind of that's the idea that I have.
Okay.
The example I have is that you read normally, then after doing it, you now convert it to linear to evaluation.
That will be painful.
How do you represent
Very painful. Exactly. Because you have to now start working with, you need to now interpolate, right? Get the coefficient form, do the division, and then evaluate back. That will be very painful. We're going to talk about it, sure. So do not be afraid. Okay, so let's just go through this example, and when we're done with this, we'll look into it. We're going to take it bit by bit. Everybody is going to follow, right? I wish I remember what we did yesterday. I'm not going to, like, as people are telling me, I'll just be writing. I'm not going to think. Eh? Okay. Oh yeah. Let's start. So we have a polynomial, and we want to prove to a verifier that the evaluation of that polynomial over this point is a certain value, right? That's because the verifier told us to evaluate the polynomial at this point, or to open the polynomial at this point, right? So what is the protocol going to look like? First of all, we need to get our commitment, right? Okay, good. We need to get our commitment. And in order for us to get our commitment, what do we need? We need our tiles, right? Okay, good. So we've gotten our tiles from the trusted setup, right? Tau of A is 5, tau of B is 2, tau of C is 3. We've gotten our tiles. Now we want to commit to the polynomial. What next? We're going to evaluate the polynomial at the different tiles, right? Okay. So we're doing coefficient form, right? Okay. So that will be commit to the polynomial by evaluating it at tau B, tau C. So we have 3, what's our tau A? Tau B, right? Plus 4, what's our tau C? So that will give us 42. Okay, let me just outline it. That's 30 plus 12, which is 42. So this is our what? Commitment. Yeah, f of tau A, tau B, tau C. So now we've committed. We are going to send the commitment to the verifier, right? So right? And then verifier tells prover to open. Right? So what does the prover do? Okay. Right? So what's that going to be? That will be 3. Right? So that's 70 plus. Right? So what is this? Okay. So now we have our V, right? What's next? To get our proofs, right? Which is a quotient polynomial. So that we can now evaluate our quotient polynomial at tau to get the actual proof, right? How do we do that?
F of x minus b over the successive
Sorry, I'm coming. We say prover gets what? The proof polynomials. Right? Okay, so we have our A equal to 6, B equal to 4, and C equal to 0, right? So what are our factors?
That's x minus 6, x minus 4.
Would that be X? Would that be X?
A minus 4, A minus 6, B minus 4, and C minus 0.
Is everybody following?
Yeah.
Sure? Okay. Okay, so we have our factors, right? We know our... Do we know our polynomial yet?
Yes. Yes.
What is our polynomial?
3
Okay. 3.
3
Is it not this?
Yeah.
Yes.
Is this not a polynomial? Minus V.
Ask for the polynomial.
I'm
Ask for the polynomial. That's what it shows now. There's
Okay.
no minus. Just
I'm hearing 72. I don't know where the 72 came from. That's why I'm asking. Okay. Minus B. Wait. Let's make some things clear. Right. We know our f of ABC is equal to 3. What was it? 3AB plus 4C. It's not this we are dividing by the factors. That's what I think. Okay. That's good. So what's our V? 72. So how do we get the polynomial that we actually, or how do we get the polynomial that all these are the factors of the polynomial? Okay. Minus V, right? So that's 3AB plus 4C minus 72. Do we agree?
Yes.
I disagree.
give us your reasons.
My reasons doesn't hold water. Okay, so so we have our polynomial, right? And I want to generate our proof polynomial. Why do we need our proof polynomial?
So evaluate that
To evaluate it at tau to get the proofs, right? Okay. So let's get our proof polynomials. Okay, so how do we go about it? Seriously? Interesting. Okay, so please tell me how I'll do it. I don't know how to divide them. Long division. So that's 3AB plus 4C minus 72. Right? We're dividing by A minus 6. Good. So what are we going to have? 3B. So 3B times A is what? 3B times minus 6. Minus 18B. If we subtract, what do we get? Okay. It's still the same thing, right? Minus 72. So, can we go any further? Okay, so this is our Q of A, right? What should be inside? Let's just make it X, right? Should it be X?
And just copy all his first quotient.
Right.
Q1. Just call it Q1.
Q1. No, I think QA will make it visually, like it will be faster for us to get, right? And what is this? A factor with respect to A, right? Okay. So, what is this? Remainder. Okay. Okay, so what is the next thing to do now? We divide the remainder by the next factor. Is that true?
Yeah. That's this.
Frankie, is that true?
You come and get more.
Okay. Oh. Okay, so we're going to divide our remainder, right?
Yeah.
By, so this 18b plus 4c minus 72. And we're going to divide it by what?
Next one.
B minus 4.
B minus 4. So, what is it going to be? Just 18.
Yes.
Interesting. So that's 18b, right? And what? Minus 72. So this guy goes off, right? This guy becomes plus minus 72 plus 72. It goes off. So we have 4c. Okay. So what is this guy?
Q of B equals
Right? And this guy is our factor, right? What is this guy? Our remainder. Okay. So what is the next thing to do? We divide 4c by c minus 0. And what is that going to be? 4. That's 4c minus 0, right? Who is this guy? QC of what? A very big question. It's actually meant to always be a constant.
Okay, so it's just
Yes, so it's just QC. If the prover is honest, it's always going to be a constant.
Yeah.
Okay, so
What of QB?
the QB is not always going to be a constant. In this case, it was, right? But it's not always going to be.
So the last one always has to be constant.
Yes.
So how about what if we evaluated A and C first?
It's still good to see.
Would our B be
Yeah,
constant?
yeah, it will still be a constant. Okay. I think I'm thinking. I was not supposed to think. Okay, so what's our proof now going to be? Or what's our proof polynomials? Let's outline our proof polynomials, right? So that we can now evaluate it at evaluate it at what? At our tiles. Thank you. So
I didn't get
okay, so like we've done the division, right? And we have our proof polynomials now. So I just want us to outline it so that we can be seeing it, right? So that we can now generate our proof. But you know, like generating the proof is basically just evaluating the proof polynomials at our tiles. Yeah. Makes sense, right? Is anybody confused up to this point?
Not yet.
Everybody's together, right? Eh? Okay, where exactly? The long division. Okay.
So is it recorded?
Yes, it's recording. I will shoot myself if it's not. It's actually recording, yeah. Okay. So, the long division, right? So, what we're trying to do is, you know, the point the verifier wanted to evaluate that if we evaluate correctly and then subtract the results, those points should be roots of the polynomial. That is this polynomial now. So we've evaluated at f of a, b, c, we got the result v, which was not 0. When we subtract that v, we are going to get a new polynomial where all those points the verifier wanted to evaluate at. V is the evaluation of the polynomial. No, you can call it any letter. Yeah, but we've been working with V for a long time, so it's easier for all of us to, like when I say V, all of us just knows what it is, right? But if I change it, we can decide to change it. But okay, no, like a formula is just a formula. Any variable can be any variable. It can be ABC, it can be x1, x2, x3. But the idea is that we know that there are different variables, right? So that's basically just the idea of abstract algebra, right? Okay, so in order to get 72, the verifier, like we had a polynomial f of ABC, right? Which is this polynomial, right? F of ABC. And the prover committed to that polynomial, right? So we told the prover, okay, this polynomial that you have committed to, evaluate it at this point. A equal to 6, B equal to 4, and C equal to 0. So we pick values for each variable. You know, if any variable did not have a value, that would be a partial evaluation. Yeah, the verifier gives the prover the values and tells him, evaluate this polynomial at these values. So when you evaluate the polynomial at these values, you're going to get a constant or a number, right? If it was a partial evaluation, you're going to get a polynomial, right? But we're actually telling him evaluate. So it's full evaluation. So it's going to get a number, right? So if that number was 0, that means A, B, and C, right? This A, this B, and this C are factors, are roots, right, of the polynomial. But if the answer we get is not 0, that means A, B, and C are not roots of the polynomial, right? So in order to get a polynomial where A, B, and C are actually roots of that polynomial, we need to subtract that value we got from the actual polynomial. So you can think of it as, when we got the polynomial, it was just a point here, right? But then it was scaled by the result we got. So when we move that result over, we are taking it out, right? So it kind of brings it back to this point. So A, B, and C, the way I'm talking about it, like if you people, well, we've not explained that graphical stuff, right? That graphical stuff will help you guys a lot. But let's not talk about it for now, so that we don't shake all the things that we have been arranging in our brain, so we don't shake it off, right? For me, it's better. Yeah, but like you can think of this graphically.
Okay, it's good thinking of it. So you want to do it for us graphically or something?
No, I can as well do that, but it will end up confusing people. Maybe after you guys have solidified the idea, then we can look at it.
Or you can meet you personally.
Yeah, or meet you personally. Okay, so once we subtract V, the new polynomial we get, A, B, and C are actually roots of that polynomial. And what does it mean for some values to be roots of a polynomial? It means that if we divide by those values, we are not going to get a remainder, right? We are going to get 0. So that's basically what we are trying to do. So that's why we now go ahead to divide by those roots, right? So we use the roots to get a factor, which is just taking it over the equality sign, right? So you know our a was equal to 6. So when we take it over, it will be a minus 6 equal to 0, right? B minus 4 equal to 0. C minus 0 equal to 0, right? So that's how we got these guys, which are the factors, right? And when we divide the polynomial by all the factors, we're expected to get the remainder of 0, right? So that's what we did here, the long division. So first of all, we divide by the first factor, which is a minus 6, right? So when we want to divide, we are looking for, like, we want to take out, this is a, right, minus 6. So we want to take out a from, like, anywhere there is a, basically. We want to take it out from the original polynomial, right? So we look for what can we multiply with a to give us 3ab. We want to take out this guy, 3ab, to give us 3ab. No, that's 3b. So 3b times a is equal to 3ba, right? Which is still equal to 3ab. Yeah. So that's basically what we do here. That's how we got this 3b. Right, so we do 3b times a, we get 3ab, this 3ab here, and then we need to multiply through, right? We do 3b times minus 6, and we get minus 18b. 6 times 3, 18 times b, right? So minus 18b, and it's a negative. So we want to subtract this, so we want to get rid of 3ab. So when we subtract it, 3ab minus 3ab, it goes to 0, right? Minus 18b is plus 18b. So that's how we got this 18b, right? And then we have 4c, which is this 4c. 4c minus 0c is 4c, right? But you can think of it as there is a 0c here. Sorry. This 18. This, you know, this you can still think of this as, let me, think of this as 0b, right? So we're subtracting this guy from this guy. Yes, this entire one on top from this guy, or this second one. Okay, that's 3b times minus 6. Yes, give us minus 18b. Makes sense, right? So when we subtract 3ab from minus, like 3ab minus 3ab, we are going to get 0, right? And then 0b minus 18b, that's 0b plus 18b, which is 18b. That's how we got this 18b here, right? And then 4c minus 0c, that's 4c plus 0c, right? Which is 4c, right? And then we have minus 7 minus 72 minus 0, which is minus 72, right? So that's how we got this guy, right? So if you look at this guy, you're going to see that there is no a term here. By dividing by a minus 6, we took out all the a terms. So we now have a remainder. We have a quotient, right? This is the divisor, right? So we have a quotient which is 3b, our divisor which is the factor a minus 6, right? And then we have a remainder which is 18b plus 4c minus 72, right? So this 18b plus 4c minus 72, we need to divide it again by the next factor with respect, that's b minus 4. So that's what we do here. B minus 4, we divide 18b plus 4c minus 72 by b minus 4. Still the same process. We want to take out 18b. What do we multiply with b to get 18b? What do we multiply with b to get 18b?
What multiply with b to get 18b? 1.
No. So we have b, right? And we want to get 18b. What are we multiplying? No. What are we multiplying with b to get 18b? 18. Right. So if we just multiply, so 18 times b. So it happens. It happens. Oh, not be skill issue. I don't know maybe your tense. Right. So it happens. People forget their names, right? Yeah. So like, if you just calm down. No, just calm down, right? So 18 times b is 18b, right? So that's why we have 18 here. 18 times b, we get 18b. 18 times minus 4, we get minus 72. Yeah. 18 times 4, 72, then the minus. Right? So we now subtract them. Right. So when we subtract them, 18b minus 18b is 0. Right. Minus 72 minus 72. That's minus 72 plus 72. That's
minus 72 times minus 72.
no. Minus 72 minus 72. Yes, minus is plus, right? So that's minus 72 plus 72. That's 0, right? So that's why these two guys cancel themselves out. And we're left with just 4c. And that 4c is our remainder, right? We're not done, right? We still have a pending factor, which is c minus 0. So we need to divide 4c by c minus 0. And that's what we do here. What do we multiply with c to get 4c? 4. Good. so we have 4 here.
Like the one you did up there when you did remove, when you did 6 times 3
Yes.
by the left, the top
This
left
one,
corner,
yeah.
that one there. So why do you not do 4 times 0 or something? When you go
Sorry, which of the
go
4?
down. When you go down now, why do you not do 4 times 0?
Wait, 6 times 3.
The 6 times 3 that you did, I gave
No.
18.
It was 6 times 3b.
I gave 18.
Minus 6 times 3b. That's what gave us minus 18b.
No, okay. So that one will not be minus 0 times 4. Not the same thing.
Yeah, minus 0 times 4.
That's 0.
Yeah, so we are doing 4 times c, which will give us 4c. And then 4 times minus 0, which will give us 0. Right. So when we subtract, we get 0. Right. So since we have 0, we divided by all the factors and we got 0. That means they're actually factors of the polynomial. Right. And those are our Q polynomials. Right. So the next thing now, I wanted us to outline those Q polynomials. Right. So when we outline those Q polynomials, we are now going to evaluate the Q polynomials at our tiles, right? In order to get the proof. Does that make sense? Is everybody together?
No,
Okay.
I'm not together.
So, which side?
So, factors. What are factors?
Okay, so basically a factor of a polynomial is a polynomial, but the factor is also a polynomial, right? Which, when you divide that polynomial by its factor, you're not going to get a remainder. You're going to get a quotient, but there will be no remainder.
Okay. Can we scroll up? Scroll up. A minus 6
Yes.
is the factor.
You know, we are saying 6 and 4 and 0 are factors of this polynomial.
Okay.
You get? So when we do a minus 6 divides and there's a remainder, right?
Yes.
But we said 6 and 4 and 0.
That was why I asked.
So it's the combination of all of them that is actually the factor.
Factors. Because if we're looking at it like, so that would mean that if we're saying there's going to be a remainder, that would mean that f of x minus b over f of x minus b divided immediately by a minus 6 times b minus 4 times c minus 0 is like there's something in my head now, but the main thing is that since a minus 6 gives us divided by a minus 6 even gives us a remainder, right?
Yeah.
It's not the same thing as saying f of x over a minus 6 a minus 4 c minus 0 won't give us a remainder.
No, f of x minus b over a minus 6.
Times b minus 4 times c minus 0 is not equals to
No, that was this thing we did yesterday.
I'm seeing why that one didn't work.
Okay.
Yeah, because a minus 6 will give us a remainder.
Yes.
Right? So it's almost the same thing as saying what do they call it? 7 over, let's say 7 over
7 over
2 times 3.
2
right?
times 3.
It's
Yes.
supposed to be 7 over 6.
Yes.
Right? But now if you now say 7 over 3.
Okay. So 7 over 3. I will get an answer,
Sorry,
right?
5 over 2, 5. So
Okay.
5 over 2 times 3. So
Okay.
5
5.
over 2 times 3. And 5 over.
Would 5 be better or 6?
No, 5 around 5.
5,
There's
okay.
something like
Okay.
yeah, right. So 5 over 3 now is equals to 2, 1 remainder 2.
Yes.
Right?
That's
No, I got to decimal. I want to show 1, then let's have the remainder second.
okay.
Right? So,
Yeah.
but if you now say 2 divided by 2.
So this will
equals
give
to
us 1.
1 remainder 0.
Remainder 0. Yes. Yeah.
You get what I'm saying?
Yeah. Exactly. That's exactly what's
So,
going on.
like,
Right? So 5 over 6 is not actually divisible,
yes.
right?
Mhm.
But when we divide it
And
and then continue with the remainder,
we end up at
we'll end up at 0.
yeah. So
That's
that was
basically
where that one didn't work.
nice. Although this is just an example, right? We need to prove it mathematically,
Yeah. We'll just like
Okay.
that.
but it's a very good this thing.
What
And
was
also Jude,
that? Okay, you brought another perspective to that.
yes, he brought another perspective to
What
it.
was the perspective?
So this is the example. He used an example, right? 5 over 2 times 3. So if you multiply 2 times 3, you're going to get 6, right? So you're going to get 5 over 6.
Yeah.
This division will not give you 0, right?
You 0 remainder 5.
Yes. Right? So we're still going to have a remainder, right? But if we do 5 over 3, we're going to get 1 remainder 2,
Yeah.
right? Then if we do this remainder over 2, we are going to get to 1 with a remainder of 0.
You're supposed to divide one divided by two. You're not dividing the remainder.
No, it's the remainder that we are meant to. This is Q. You can think of this as Q, yeah, and this as the remainder. Right. So it will be good to like use abstract algebra to like prove it, right? But this is like a very good example for why it doesn't work.
For why what doesn't work?
For why when we multiply, like what we were trying to do yesterday, where we were doing a minus 6. You can think of a minus 6 as 2, and then like b minus 4. You can think of b minus 4
What if you
as
are done
3.
it the other way around?
Eh?
What if you are starting with 2, then did 3 next?
No, it will still
Can we try that?
okay. So that will be still a 5 over 2 times 3, right? So we have 5 over 2, which will give us 2, right? Remainder 1.
If you divide by 3,
Interesting.
now it's 0.
Okay. Okay. Oh, actually.
So this case is different from that.
Yes, it's different.
Oh,
You know, in our addition, do the first time right?
No, but it can be.
In our division, right? Either way to do it.
I think the reason why it's not working is because
Yeah.
I don't think 2 and 3 are factors of 5.
That's the thing. The same thing with that other one. A minus 6 alone is not a factor.
It is.
One of
It's
the
a factor.
It is not a factor.
No, alone. Alone is not.
Alone it is not a factor.
But with
It's a
the
factor
factor
is
is-
No, even when we subtract v, alone is not.
it's not a remainder.
Even when we subtract v,
Factors.
Yes,
Factors are supposed to, like, if you divide by all the factors, it's supposed to end with 0.
yes.
So, no matter how you go through, and what makes up the factors, so you should look at this 5 and 3, I don't think that.
No, but
2 and 3 are not factors.
the idea is that a minus or a on its own, right, is not a factor. Like all the variables have to be. Like, because if you divide by just a, you're definitely always going to get the remainder in the remaining number of variables. What does dividing by a mean? It just means taking out a, right? So if you take out a, you're going to have something in the remaining number of variables, definitely, always. So it's when you say this and this and this, all of them are working together, right? It's just like the Boolean hypercube case, right? Where you're trying to get the Lagrange basis, and you're saying 0 and 0 and 1, right? Your Lagrange basis polynomial is going to be, let's say we have 0, 0, 1. It's going to be check 0, check 0, and check 0, and check 0, and check 1. Right?
One thing to say was that we divided yesterday, regardless of how it started, we are always going to end up with that last R being 0.
Yeah.
So if you are started dividing with a minus 6, or if you are started with b minus or c minus, you are
Yeah.
always
Going to end up with
R
one.
equal to 0, which
So-
is not
but-
the case here.
But this case is because 5 is not a factor.
If you want to reduce 6,
If we add 6, it should work. Right.
This is
Okay, let's use 6. So that is, sorry, this is exploratory, right? That is the idea. That's why we are here, right? We don't know what we'll discover when we are doing this. You may just discover the next post-quantum secure proving system. Actually, okay.
meanwhile.
Okay, so we have 6, right? Divided by 2 times 3, right? In short, like with the first division, we're not even going to get the remainder, right?
yes, we won't get to
Yeah.
So I
So
think
2 is an independent factor of 6. Unlike our case where all of them together.
Together.
will be factors.
so.
Yeah.
So what I'm thinking is normal numbers, like natural numbers, they are always independent factors. There is no factor that depends on another factor. That is what I'm thinking about. Like 2 is always a factor of 6 over its own. what I'm saying is, there's, okay, for instance now, for our own polynomial, a minus 6 is not an independent factor because it depends on the rest.
Yeah, it
So
depends
it can
on
become
the
a factor of x, f of x and everything. But in this case now, it's difficult to find another number that you use to divide. Let's say you have a number, a normal natural number, you have a random natural number. You can't divide it with another random natural number that is not a factor. That will not, shit, what is this? Here is this. Okay, you can't divide it with another natural number. And let's say that other natural number is, you now say it can only be a factor of other number if it can only be a factor of the other number if you multiply it with a different number. It is either it is a factor, it is not a factor. That is just
So you can use like rational number.
okay. I don't know about that one. I don't know.
Isn't 2 a factor of 6? But it depends on
For example,
No,
now,
it doesn't depend on
No, it doesn't depend.
It
Like
doesn't
2
depend.
times.
They are independent.
there's only one
It's
other
actually-
factor.
it's actually-
Divide by
No,
times
it's-
by
But-
2
No,
is
it's a factor because if 2 goes into 6 straight times to mean that's 0.
That's-
That's just,
It will always
Is the-
remain as zero.
it's because it's a remainder of 0, that's why it's a factor.
Yeah.
Is it not factor times factor? I guess it is.
Yes.
No, like you can multiply.
Is there another number I can multiply by 2?
Natural numbers now, okay? Natural numbers. No, what I'm saying is 2 is a factor of 6 because there's a remainder 0. It doesn't
Yes.
matter the quotient. Leave the quotient. It's always a factor. I'm saying,
No, like a factor, right? A factor is that when you divide, you get a remainder of 0.
Yes, but like there's a factor table for every number. 30 now, factor of 30, 15 and 2, 12 and 15 and 2, 10 and 3, 5 and 6. Those two are like each factor is a factor because when you divide 30 by 5, you get 6 remainder 0. When you divide 30 by 6, you get 5 remainder 0. Like they both are factors because when you multiply by 1, you get 30. And when you divide 30 by each number, you get the other factor remainder 0.
But you, 2 independently is a factor because when you divide, you get the remainder of 0, right? The quotient can be 3, you get. But what we are interested in is that remainder, that it doesn't leave a remainder.
Okay, meanwhile, this one
Like if 2 was not a factor, then it's going to leave a remainder. That means, let's say maybe 3 over 2, right? So this will be 1 remainder 1, right? So in as much as this, there's this 1 remainder, we don't care about this guy. In as much as there's this 1 remainder, that means 2 is not a factor of 3, right? But like, okay, let's go back. Okay.
What's the relationship between the factors and the points that the verifier tells you?
So when the verifier tells the prover to open at some points, it's possible that those points are not factors of the polynomial.
They are not always factors.
In most cases. In most cases, they are not always factors. So we now need to get a polynomial that those points are actually factors of by doing that polynomial minus the result. Yes. Which is that f of x minus v. Right. So this minus v will now give us a polynomial where those points are factors. So when we now divide this polynomial by all those factors, we are going to get 0 as a remainder.
So is that what we're doing?
Yeah, that's why we're doing this.
Because I noticed that the factors you said a minus 6 one of the points, and then 4 2 and then 0 2.
Yes,
So I was wondering what was the relationship.
between them. It's just like the points we wanted to open at. So, okay, these are the points.
So are we going to always do a minus points?
No, see, like this is, if this was minus 6, then minus 6 will move over the equality sign, so it will now be a plus 6. Makes sense. Okay, guys, are we together? Eka, are we together?
Yes, sir. Like I'm following back to back to back.
Okay. Okay. So let's go back to what we were doing, right? We have a factor which is a minus 6, right? And what was the corresponding q? It was 3b, right? How about b minus 4? It was 18. How about c minus 0?
What we are trying to do now is what?
Just to outline
Okay.
our q's.
Okay.
Yes. Our q of c was what?
I think 4. And you
4, yeah.
Yeah,
4.
it was 4. So, we're expected to now evaluate this polynomial at tau's.
Each of them.
Yeah.
Yes.
But Q of C is a constant.
Eh?
Q of C is a constant.
Yes. If you evaluate a constant at any point, it's always going to give you that constant.
What about, okay, 18 is a constant.
Yeah, 18 is a constant. 4 is a constant.
Will it give you 0? Will it give you that number to be 0?
No, it will give you that number. It's just like you drawing a line. Anywhere on that, like you have a graph, right? This is 15, this is 16, this is 17. Right? These are lines, right? So, if we are talking with respect to the y-axis, even if it's here you pick, the y value is still 15, right? If you pick here, let's say this is the x-axis, right? It's 1, 2, 3. If you take this up here, it's still 15, right? If you take this up here, this is still 15. If you take this up here, this is still 15, right? So it's kind of a constant. You can think of this as a constant line, right? Irrespective of any x value you pick, it's going to give you the y value of 15. Does it make sense? The graphical is beginning to seep in, but
You get now, you're not asked for that.
okay. So what's our taus? Our tau values 523. Right? Right, and this polynomial 3b, right, when we evaluate it at, it's a polynomial with respect to b, so it's tau of b we are supposed to use, right? So that will be 3 times 2, which is 6, right? Makes sense?
Yeah.
Sorry, can you say that?
Okay. So this is 3b, that's a polynomial,
Yeah.
right? And what is our tau value for b? 2, right? So we are going to evaluate this 3b at 2. So we're just substituting.
Yeah, but why do we choose to use 3?
No, this 3b was what we got when we divided. So this is 3b,
Yeah.
right? And this b minus 4. This is its own proof, right? and this is C minus 0. This is its own. Right. Okay. So that's why we outlined it here. So these ones are constant. This one was 3b. So we had to evaluate it at tau. If we evaluate this one at tau, at let's say tau of C, we're still going to get 18. Right? And this one is always going to be a constant. Making sense? Sure? Okay. So now we have our proofs. Our proof with respect to A, proof with respect to B, and proof with respect to C. We send these proofs to the verifier together with V, which is the actual evaluation of the polynomial at the point he told us to open the polynomial apart. Right? What were those points? Was that equal to 6? B, 4, C, 0. Right. Okay. So, with this, so what was V again? So we send V equal to 72 to the verifier, and then he asks us prove it, right? And we send 6, 18, and 4 as our proofs. So, yes, 6, 18, and 4. Yeah. So we send it to him. He said we should prove it. We send the proofs. So now it's time for the verifier to verify, right? And in order for the verifier to verify, what does the verifier do? We have our f of A, B, C minus V, right? And it should be equal to tau minus A, tau minus, okay, let's call it xi, that'll be x1, x2, x3. Minus V, right? And it should be equal to, say, tau minus xi, right? Is it all? Well, I meant to sum, right? So, mathematics and notation. Okay, so so this is what the verifier wants to check, right?
So what is not f of now? Why not tau A tau?
Actually, okay, since we are using tau here already, right? Right? So tau of 0 up to tau of n minus V, and we're starting from I equal to 0 up to n.
What would be xi? Is it the A, B, and the C?
Yes. So this is basically still the same thing we've been saying, right? This is the commitment, right? This is the evaluation, right? This is the factor, right? And its corresponding proof. Yeah, one of the factor. and its corresponding
So
proof.
it's going to run based on the number of factors.
Yes, based on the number of factors. Based on the number of variables, which is basically the number of factors. So we are going to do this summation. Is it making sense?
Okay, yeah.
Sure.
So what we are doing here, we are just replacing x with we are replacing x with tau, or let's say a with tau.
We are replacing tau with the actual value of tau,
Yeah.
right? And x with the actual value of x. So I can be either A, B, or C, right? Based on what we've been working with. Right? So it can be tau of A, x with respect to A, Q of A. Right? It can also be tau of B, x with respect to B, and Q of B. Right? It making sense? Okay, so this is what the verifier wants to do. Right? What is our commitment? 42. So that's 42 minus 72. And it should be equal to what? Okay, so let's start with A, right?
Francis, please can you show like
Where?
where you got the Like which ones you know where you got the
The 42.
What is the commitment?
Okay, yes. So it's so I'm evaluating the polynomial at all value of like all the taus. This is it. This is it. So that is the original polynomial I evaluated at all the values of this are tau. These are taus were gotten during the process setup. In the process setup, or no, the process setup. For now, let's not think of how the process setup works. Let's just know that the process setup gives us random values for tau. So it just gives us random values for taus, and those are the values we use to actually commit to the polynomial by evaluating the polynomial at those values of tau. Makes sense? Okay, so we have our commitment, which is 42, which is the original polynomial evaluated at all those values of tau, right? And then we have our v value, which is the polynomial evaluated at the point the verifier wanted to open at, which in this case is which is a equal to 6, b equal to 4, and c equal to 0. Yeah, that's what we used to get 72. Right. Okay, so now we want to do this other side of the equation. Yeah, that's basically what the equation is. If you want, you can do minus 72 plus 42.
If you are changing it, means you are changing the signs too.
No, you are retaining the signs.
Like, what if you change it 72 and you put that plus?
72.
Yes, like you bring 72 to the left side, to take on to the right, then you don't put that plus.
Then you don't put that.
Maybe minus.
No, no, no. It's not. This is not actually minus 42, right? It's plus 42. Yeah.
Oh, so each number is carrying the
It's sign. Each number has its own sign. Yeah. Makes sense. Okay. So 42 minus 72. Alright. So next, this other side of the equation, we need 2. We need to get it. Are we together?
Yes.
Eka. We are together, are we?
Yes, yes, sir.
I trust him. Okay. We are together, are we? Okay, good. So now we need to face this other side of the equation, right? And it's a summation over all the variables. Right. So we are going to have each of this thing for each variable. So let's start with A. Right. What's a tau of A? A tau of A is 5. Let me just. Should I bring this thing down here? Okay, so a tau of A is 5, right? Minus, what is our A? 6, right? This part confused some people yesterday because a lot of numbers are moving around and it's understandable. So people should pay attention, right? So, what is our A? 6, right? Times, what's our Q of A? 6. Our Q of A, our A, and our tau of A. Right? 6. Good. So we're going to add it to. Let's go for B, right? What's a tau of B? 2, right? What's our B? 4. And what's our Q of B? 18. So that will be 2, right? 2 minus 4 times 18, right? So for our C, what's our tau of C? 3, right? What's our C? And what's our Q of C? 4. So 3, 0, and 4, right? This makes sense. What is the left hand side? What do we get? Minus 30 is equal to, yeah, minus 6 plus minus 36, sorry. Right? So plus 12. Sorry. Right. So this is it's equal to 30, right? And since it holds, the verifier
Accept.
accepts, right? Does what we did make sense?
And the verifier is not the case where the verifier is not convinced.
Yeah.
Accept, you know.
So he accepts.
So I used to. I know it. I want to write.
Is it okay?
You said
Yeah.
accept, yes. You said
Don't worry,
accept.
I want to write it down.
Is it okay?
No, I'm not writing it right now.
Is it okay? Huh?
Yes, yes, it's okay. It's not okay. That's nothing already.
Huh? Don't worry.
It's not that good. As I'm saying, you will do that.
Okay.
Thank you.
So
You said something like accept.
the verifier accepts.
Accept.
Yes. Since the two sides of the equation are the same, the verifier accepts.
This is what's the name of the side of this equation?
Does it have a name?
The left side of the equation that you keep. Go back, go up. Yes, this left. What is it called? What is this? This is polynomial. This one is left side.
This left side.
This F, tau.
This one.
What is that for the equation called?
And
The
left.
evaluation of tau minus
Then this one.
Okay, I thought you were looking for a
This
name.
side is the
Like,
running sum
Only
of
some.
it's the running sum of the tau minus
the factor,
the factor times
the
quotient.
corresponding quotient.
So like, that's the name.
It just
The name, like,
that's what it
Then
is.
it's what can help me remember actually. That's what I'm like. So if I want to like, okay, you have to get 30 now. You did the coefficient of tau.
the commitment to the polynomial minus the evaluation of the polynomial.
Okay, the commitment of the polynomial minus the evaluation of the polynomial. So
Yeah.
that's how we arrive at the 30.
Like, I don't think, like, basically, for me, I don't know about other people, right? But if you understand the fact that when we have f of x minus v divided by x minus a, we get that q of x plus r of x. With this, everything just clicks, right?
All these times are so
Yes.
I mean, I get this fx and that's the one that so this qx that's what you showed us, that's the one that left.
No, that's the one I did. This qx and rx, right? Rx will always be zero if the prover is honest, right? So we can think of it as not being there since we expect it to always be zero. So what we just do is just cross multiply, right? This guy goes here, this guy goes here. So that's f of x minus v is equal to q of x times x minus a, which is basically the same thing.
Okay, this is for univariate.
Yeah, this is for univariate. But if you understand this for univariate, then you also understand it for multilinear.
It's the same
Right.
for
Yeah? Sorry.
Wait there. Don't worry, I'll see.
Does it make sense? Huh?
It's trying to make sense. I'm trying to compare, I'm trying to think of how that f tau stuff.
So this.
Yeah, like how you derive it to give that one that we just saw, just that f bracket.
I think, like, you may need to rewatch that first KZG video. I think we no last week. I think last week Monday, right?
I don't want to know. It was like
Yeah, it was Monday.
Wednesday or Thursday.
No.
Oh, okay, I think you started Monday.
Yeah, it was Monday I started. So like we basically looked at it and why it even works, right?
So I don't know how you derive that one from this. This one that's up now. You said that you derive it from this one that's down right
Yeah.
there. Derivation, how you derive it from this. Okay, so basically, like I want to solve, I'll just skip to that one. So that's the one is.
No, this one is for univariates.
Okay,
Yeah, but that one is for multilinear.
not up for multilinear.
Yes. Are we together? Sure. What's up with this thing now? I beg. Okay, so
Beating us for what we do.
okay. Actually, let's look at evaluation form now. What is it? 11, 16. So let's look at evaluation form. Are we ready? No, it's not. It's not so difficult.
Like, this evaluation form will be used in it.
Basically, like your polynomials are in evaluation
So
form.
I
Right?
want to think of this that point. That one I will just do that, it's not important.
Ah.
No, now you say I think evaluation form.
How do you want to understand this one if you don't understand that one? That one is what should help you. Yes. That one is what makes more sense. Right? So that one is what actually makes more sense. Right? Now we're working in evaluation form. It may not be so straightforward like what we've been doing.
Let's
I
continue.
pray.
Surprise you.
I pray. Like when I and Wilson were trying to work on the division algorithm for the evaluation form, it took us to set theory.
Huh?
Yes. It took us to set theory. Okay. So let's go, right? We're still going to do the same thing, same polynomial, same taus, same evaluation form, same evaluation points, right? But
When you get to the part that helps you, like, when you get to the part that set theory help you solve things.
the set theory side. So actually, like, okay. I'm trying to look for a way to explain it that won't take us that way. Because if we go that way, some people may get lost. You get. But that is actually the best way to think about it.
When we get lost, we can't find
See, can you just come out with this? Right? Then you have to go smart.
Yeah.
Just let me derive. Just try and derive this.
Okay. So we got the like after looking at this thing, we got the formula, right? We're trying to understand why does the formula work, right? So when we're trying to understand why the formula works, we actually found out that it's somehow related to set theory. Yes. So, like the whole Venn diagram stuff. Yeah. So,
You know, we opted for
no problem, Abi. Okay. There's normal Venn diagram. Yes, a non-intercept.
Analysis.
Okay. Okay, so maybe when we get there, you will help us.
But you recap, you reiterate that stuff that was like, no, this is like most people. Like 2 decades ago.
No, but I thought you said you'll be the one helping us.
This is like 2 decades ago.
Okay, no problem. Okay.
when we were doing multilinear evaluation, we opted for the evaluation form because it's made it faster.
Yeah.
Why is it the same thing for this one also? Why we are opting
For the evaluation
instead
form.
of the competition?
You know what? So the thing is, because we're already working with the evaluation form, we have to work with the evaluation form. So it's just like all these different protocols, right? So a protocol working with univariate polynomial, has in the IOP, like a univariate polynomial IOP, cannot just switch to a multilinear polynomial commitment scheme. I don't know if what I said makes sense. You know, when we're talking about a snap, we said it's what? An IOP plus a PCS, right? So if your IOPs work with a univariate poly, right? That means your PCS should be univariate, right?
Which IOP works with univariate?
IOPs that work with univariates, we have the Plonkish,
Plonk.
yes,
Oh wow.
yeah.
What was that? What's that?
Interactive oracle proof,
Interactive oracle proof.
yes.
Too many information.
GPR is
Yeah,
GPR
yeah, you can. It's interactive,
Why are we calling it that?
but you can make it non-interactive.
just use something.
Most of these protocols are interactive. We use fiat Shemer to make it non-interactive.
So which shard now? Is Fiat Shaman only the only way to move from that to non-that?
Is the known way.
You can invert from
There's many
Eh?
mailing.
Mailing.
Then one mailing.
Mailing is an implementation of a transcript.
Yeah, like similar to
Fiat Shemer is the process, is the protocol. You can decide to implement it anyhow, right?
So the mailing is a way of implementing Fiat.
It's an implementation of Fiat Shemer.
I think it's
transcript.
The Fiat Shemer is the process of rendering an interactive protocol non-interactive. Yes. Yeah.
So the mailing you're talking about now
The mailing is an implementation of the transcript.
So it's like a pattern of implementation.
Yes. So
Like
your
mailing implementation.
yes, the mailing implementation of the transcript. People have your own implementations too, right?
The one we use
Yes, the one we use Capactify.
I thought mailing will be hashing and doing
No, mailing is not hashing.
What
So in
about-
the
what about patterns like this?
in the industry, it's mostly the mailing transcript that a lot of people use.
Industry standard is
commonly used in the industry.
What makes it what it is?
Eh?
What makes it what it is?
Like why is
it like?
I think it's the way they went about the implementation. It's quite similar to what we have. Yes, it's quite similar to what we because we actually the idea was gotten from like both the mailing implementation and also like I think Lambda works to have their own transcript implementation. Yes. You get so different people have their different implementation of the transcript. You get. Are we together? So we have the IOP and the PCS, right? And if your IOP is a univariate polynomial, works with univariate polynomial, your PCS also has to work with univariate, right? If your IOP works with multilinear polynomials, your PCS also has to work with multilinear. But currently, with the way the space is going, there are IOPs or there are PCS that can actually work with both univariate and multilinear. Something like, I think, base fold.
Base fold.
Yes.
It's an IOP.
No. It's a PCS.
Okay.
So base fold is a PCS.
Which IOP can work with both? So any of the IOPs that works with univariate can choose to work with the base fold univariate. And the one that works with multilinear can choose to work with the base fold multilinear.
So actually, base fold combines, like they use sum check, which is basically a multilinear, like sum check works over multilinear polynomials, right? And then they combine sum check with fry. Fry is a polynomial coefficient scheme.
I thought some check is an IOP.
No.
Subject is like a protocol. Yeah. Right. So they combine sum check with fry in order to commit to a polynomial. That's base fold. Right.
Wait, this question he asks now, like some check is trying to prove something, right? Right?
Yeah.
And it's also an interactive thing. So why is it not an IOP? Because GKR, one of the reasons why GKR is GKR is because it uses subject. So I don't know.
Actually, like we can also think of sum check as an IOP, right? Because we have multiple rounds, right? And the final round, the verifier does an oracle check. Interactive oracle proof, right? But so you can think of it as an IOP.
Why
You
did I
can think
ask
of
you?
it as an
So that maybe when we want to talk about something and want to talk it with full
we have
chest,
full chest.
so we talk it the same way and not the same nonsense.
Yeah. So sum check, then GPR works with sum check. This is the sum check.
Both subject and GKR are IOPs, but GKR is dependent on some check
Sum check.
to make it.
A use case. No, it's not the only. Yeah.
So some check can stand alone
Without GKR.
Without GKR.
Yes.
But GKR cannot stand without subject.
Sum check makes GKR possible. Like sum check makes GKR possible. Right.
You have to understand subject in order to make it.
Yeah. Yes. The other IOPs that will work with like sum check have Spartan.
Spartan.
Yes.
Ah,
Actually. So the Spartan IOP it works with sum check. Right.
Facts.
But it's, I don't want to go into this thing.
Okay, let's continue.
So, in essence, the bottom line is proving the evaluation of a circuit. That's the bottom line, right? A circuit can be a program, right? But that program has to be constrained. You can have a program and you convert it to a circuit by constraining it, right? Then you now need to prove the execution of that circuit. A normal program, your Rust program, your Python program, you can convert it to a circuit, right? And converting it to a circuit is basically writing constraints that must hold. Like, in order for that program to execute correctly, these constraints must hold. That's basically what a circuit is. A circuit is just constraining your program, right? When you've written that circuit, the idea is now to prove the circuit.
Can you convert smart contracts to circuits?
Yeah. Any program, basically. Right. A circuit, what is a circuit? You're just writing constraints. So, in your smart contract, you use assets, right? What is asset? Asset is a constraint. You're saying asset equal to. That's a constraint, right? If that constraint doesn't hold, it will fail, right?
Oh, so it's like this the circuit is like what we just said. The circuit is putting it's not the circuit is not actually executing, it's just putting like different plenty assets at different positions.
Yeah,
Like
basically.
checking.
So that, yeah, you can think of that as a circuit. You're putting a lot of like checks. This plus this should be equal to this. It must be equal to this. This plus this must be equal to this. This plus this must. This times this must be equal to this. This times.
Is it like, for example, the proof and
No, I've not even talked about proving it.
what's an example of
Reading the circuit.
Huh?
What's an example of constraint?
An example of a constraint: A times B equal to C. Numbers.
No, I mean in the like smart contract, like
So you can say a person's balance must always be greater than or equal to 0. That's a constraint, right? Or previous balance minus current withdrawal should be equal to the current balance, right? It's a constraint, right? So constraints are just checks. Like this must hold, this must hold, this must hold.
Not like the entire
So if you
contract
were to
itself.
write a, if you were to
Eh?
write
It's not like the entire smart contract itself.
so if you were to write a circuit,
Like, if you're writing a program as a circuit, all those constraints that must, like, you need to rewrite the entire smart contract in a way that all those constraints should hold. So if all the constraints hold, that means that smart contract executed. Does it make sense?
So that I think
That
means, you know, you said that for to get any constraints system, you have to identify the problem, a statement or something. So as part of that statement, you are going to like
Arithmetize.
constraint system. So,
Yeah.
okay. So not necessarily the assets, just the old smart contracts.
The logic.
What is the logic?
Okay.
The logic is actually those assets, right? in your smart contract, you get a person's balance from storage. You check if the balance is greater than or equal to the amount the person wants to withdraw. Right? If it's greater than, you throw an error. You can't withdraw so and so amount. Eh? Yeah, but like maybe asset is too harsh, right? Yeah. So the idea is that is where the concept of witness come in. The concept of witness.
Okay. No, only for me, I was witness from like normal photography. Normal photography, like witness, like the output of the hash is a witness, right?
If you're thinking of it in terms of a circuit. Maybe let me just digress.
Wait, I
Wow.
don't understand smart contracts. What are we
You don't understand matrix multiplication.
Okay. So let's do a basic example we did initially a long time ago. No, but we're not going to not smart contract now, just a polynomial. Just the evaluation of a polynomial, right? We are going to write a circuit, or we are going to arithmetize the evaluation of that polynomial, right? We are going to arithmetize the evaluation of that polynomial. Let anybody give us a random polynomial? Eh? Which one? Okay, that old one. I can't remember the polynomial actually. You have it. Eh? 3ab plus 4c. This will require multiple inputs. Let's use something that requires just one input. We can still do it. We can still do it. Should we do it?
We have used before so that we can trace the similarities and the differences.
For a start, let's do it small.
No, starting. What do you guys think?
Should we use a univariate polynomial or a multilinear?
Wait, you're not in the evaluation form, are you?
Yeah.
No, that one like
We are not doing evaluation form.
What are we doing now? What
What
are
is it go?
Is it the evaluation form?
I think you want to say.
No, we're not doing evaluation.
actually I think let's not do
Let's
it.
do our evaluation.
Right.
Anybody that doesn't understand, let them come and meet you.
Let's go smart contract.
Let's go back. Like all these things we are talking about now are things we intend to. These are things we intend to talk about after you guys have finished your succinct GKR. Like
So, okay, so
yeah.
Sorry, I thought you were talking about one second.
Okay, no, it was the circuit that was. Well, I think let's just let's not digress. We're still going to talk about it when everything has settled, like GKR, like all of you are okay with GKR and your succinct GKR implementation is done. We're going to talk about all those things like R1CS, Blankish arithmetization, like I'm going to just talk about all these things. Okay, so back to business. That was about 30 minutes of digressing. Okay. So, what's our polynomial? 3ab plus 4c. This polynomial has three variables, right? Let's represent it in evaluation form. Right? So this 3 right? Right? Interesting.
After you finish, you
Right? So what's our polynomial? Yeah? 040404. Okay. This is a polynomial, right? And these are the points we're evaluating the polynomial. This equal to. Just evaluate the polynomial at this point. So this 3 times 0, everything here is 0. 4 times 0, 0, so we got 0. This 3 times 0, 0. 4 times 1, 0 plus 4, that's 4. This 3 times 0 plus 4 times 0, that's 0. So basically that's just what we did for all of them. 3 times 1 times 1 plus 4 times 1. Makes sense? Okay, so this is a polynomial in evaluation form. Right? What was... Okay, let me get...
Tau A
yeah.
is 5, tau B is 2, tau C is 3, A is 6, B is 4, C is 0.
Okay. Okay, so what are we supposed to do now? Right? What is the next step? We have our polynomial. We have our taus. What is the next step? We need to commit to the polynomial. Why is everybody lost? Eh? Sorry? Right now, yeah. 1 minus, okay, yes. Yeah, that's check 0. So we have our taus, right? So we need to generate our trusted set of parameters.
Trusted set of
Yeah. But how can we evaluate? What is the idea?
Okay.
So I want to do a dot product, right, of our polynomial evaluation form and this what? Eh?
Why are we doing dot product?
And it's Lagrange basis. You know, in the univariate polynomial case, we're doing a dot product of the coefficients of the polynomial and the powers of tau, right? But now this is the evaluation form of the multilinear polynomial, right? And we actually wanted to separate tau values from the evaluations. And how did we do that?
We did, we write the Boolean hypothesis and reduce the interpolating this. Like check 0, check
For each
variable.
So what is that?
What check?
No. We are trying to get another array, right? We have the evaluations. And we're trying to get another array such that if we do a dot product of the evaluations and that array, we are going to get the evaluation of the polynomial, right? What is that second array? In the univariate polynomial case, we're calling it powers of tau, right? Because we are working with the coefficients. Now we are working with the evaluations in multilinear case. What is that array? Say it with confidence. Eh? It's the Lagrange basis, right? What is a polynomial?
Polynomial.
Summation of polynomial.
A summation of monomials, right? That's right. Right. If you want to think of it in the monomial basis, it's a summation of monomials, right? But if you want to think of it in the Lagrange basis, it's all these things I'm saying making any sense. When I say monomial basis, does it make sense? In terms of monomials, that is the coefficient, right? Right. Then, when we want to think of it in terms of the Lagrange basis, we're thinking of it as evaluations, right? And then the corresponding Lagrange basis. So we have y times, we have a summation, y times its corresponding Lagrange basis, right? Let me just write it. We said this thing yesterday. Right? Eh? Okay. I understand. I understand. Is it how they write it? Anyhow they want to write it, let them write. Yeah, I'll call it, we'll write our own. Thank you. So, y times is Lagrange basis, right? So, now we need to get that Lagrange basis, right? And how do we get it? Let's get it here. Tau of B 2, right? And tau of C 3. Okay, so we want to get the Lagrange basis, right? So what's that going to be?
For the first one.
Yeah, for the first one.
Tau A.
1 minus tau A. What is tau A?
5.
5.
Minus tau B.
Okay. Right. Okay. What's the next? 1 minus
1 minus 5. 1 minus 2. And 3.
and 3. Right. What's the next?
1 minus 5. 2 minus 3.
Okay.
1 minus 5. 2 and 3.
Can you people see any pattern? Continue. What next?
1 minus 5. 1 minus 2. 1 minus 3.
People cannot see any pattern.
I'm not seeing anything. Current indexes for each.
5.
5.
Yeah. 1 minus 2. And then 3.
Yes, now. 1 minus 5.
Okay.
5 again.
Okay. Okay. So basically, like the pattern I just wanted people to notice is that we are doing this computation how many times? We are doing it here, we are doing it here, we are doing it here, we are doing it here. Right? Yes. And we are doing it here too. Right? This computation, we are doing it here, we are doing it here. We are doing it here, we are doing it here.
Oh, normal, our theory.
Yeah. But the thing is that if we do this computation, do you want to do it multiple times? This is all the senior developers in the house. So, like, for now, right? For now, the idea is just people should understand it and implement it. But when you now want to optimize, your code, you can use maybe dynamic programming, right? You can use dynamic programming or let's say any other programming technique in order to avoid doing this computation more than once. Right? There are papers that have been written on just this. How to do this efficiently. There are papers that have been written on just this. How to do this efficiently. Does it make sense? Okay. So, put on your maths hat. It's on, right? People have done it. Oh shit. Okay, so what is it? What?
Minus 8.
Minus 8,
So
12.
24 minus 22.
Should we break it down?
No, just it's okay.
Okay.
Is it minus 24? No, minus 24. Minus 24.
So 84. 32.
Minus 32. Sorry, it's minus 24.
It's not minus 24.
Break it down.
This will give us minus, right? Minus will give us a plus times 2. So it's going to be a positive.
Minus 30.
Okay, minus
Tenth
30.
one is
Math
It's 16, not 64.
You said two.
The third one.
yes, it's minus 8 times minus
5 times 2 times.
And this other one is minus. It's minus.
Minus 4 times minus 2. That's 8. Right. Times 2. 16.
This one is now
3 times 2. That's
that one is now minus.
minus 24.
okay. So this minus 1 times minus 2.
Minus 10.
No, not minus 10. Okay. So this is 10 minus 20.
For that first one, why is it 8?
Maybe it's 25.
Okay. Okay. Okay, let's calm down. Yep. Sorry, I'm coming. Let me copy this. Okay.
I did now, I'm getting a mistake.
We're getting minus 9. Okay, let's look at it. Stop. It's okay. Stop. Okay, so this 1 minus 5, that's minus 4, right? And 1 minus 3, that's minus 2. So minus 4,
1 minus 2.
that's minus 1.
Okay, minus 1.
Yeah. So 4 minus 4 times minus 2, that's minus 8. Sorry, that's plus 8, sorry. Then times minus 1, that's minus 8. Maybe you're not using brackets. You need to put the brackets. Right? If you don't put the brackets, it may multiply first before adding. Okay. Are we together?
Yeah.
So these are our evaluations, right? Do we agree?
Yeah.
These are our what? There's a name I'm looking for. The Lagrange basis, right? Okay, so let's just outline it. So that's minus 8. Please just be calling it for me. 12, 16, minus 24, 10, minus 15, minus 20, 30. Right? Are we ready? Okay. Wait, what is the value of our commitment? What are we expecting? 42, right? Okay. So this will be 0, right? This will be what? 48. 0. Okay. Plus element-wise multiplication. So 7 and 30, 3 and minus 20, 4 and minus 15. So we just multiply them element-wise. Make them. Then we sum. Yeah. So what was it?
It's 258 minus 16.
42. Do we agree with him?
Yes.
You always agree with doctors.
Is this something?
It's correct.
Are we? 42, right? So 42, it matches our commitments.
So what we call the
Which one? This one? This one? Okay, the Lagrange basis. Yeah, but in the main protocol, yes. In the main protocol, this will be G of tau. You get? In the main protocol, this will be G of minus 8, G of 12, G of 16.
if we did not know how, are we going to like get this?
Yeah, we're still going to get this.
If we know that we just get this and work with this without seeing our
Yeah, without still knowing our tau.
The small issue I'm having is the fact that, see, we are working with 3 variables. We have to do that computation. That one that has to do with
This one.
yeah, you have to do this computation. How about when you are working with 8 variables and 10, 20 variables? It's going to take a lot of processing power on the system.
Even if it's 1 million variables,
yes,
you still need to do this. So that is why I said there are papers that were written just to optimize this.
I'm saying that. What about when we monitor? You know how to do this?
When you don't know tau, no, we're still going to. This is,
Yeah, I didn't talk about it.
yeah.
So what if we don't know that?
If we don't know tau,
Because the example we did now, you said that we are just doing it because we know how. Things like that are the same. What if we don't know how? What are we doing? Just like
if you don't know tau, like, basically, we're still going to look at that process setup, right? But the first person that actually contributes, the person that initializes the process setup, will know the person's own tau, right? And then the person is going to do this computation and then encrypt the values, right? So what the person will be sending will be G to the 1 minus 5, 1 minus 2, 1 minus 3. The person knows this. The person knows the person's own tau, right? Like the person that initializes the process setup,
okay.
right? The person knows his own tau. You know, everybody that contributes in the process setup know their own tau, right? So the person that initializes the process setup does this, gets these values. Basically, when the person does this, the person is going to get this array, right? And then the person is going to encrypt it to get G of minus 8, G of 12, G of 16, G of minus 24, G 10, G minus 15, G minus 20, and G 30. Right? So this is what will be returned in the process setup. This array. Yes, sir. Like this array is what will be returned. So here is actually this array we will now be working with.
Are we doing the process of the last one? Are we going to add that function?
To do the process setup.
Yeah,
Is it in your tests?
yeah.
Okay, normally the process setup is usually done, right? So you can actually implement the protocol to enable people contribute. But you know, when we're looking at the process setup yesterday, so it was yesterday, right? Where we now has the issue of when somebody wants to contribute to this. If, like, I instantiated the trusted setup, I've gotten this guy. If another person wants to come and contribute, it's expected that the person will do this for the person's own tiles, right? And then the person is going to, after the person gets this array for the person's own tiles, the person is meant to now multiply this our own with the person's own. The person's own tile in the clear, right? Which are these values themselves for the person. Is it making sense? Is it making sense? All of us will seem lost.
You're supposed to get 1,000 over million accounts.
Yeah.
For each contributor must add entry.
So each contributor is meant to add the person's own randomness. Yeah. But now we know that tau is actually multiple taus, right?
Yeah.
That was the issue we had yesterday, because if somebody generates the person's own array, let's say this is 2, 5, 8, 12, 16, blah blah blah. If we multiply it with this, then we'll be getting like g to the minus 8 to the 2, right? G to the 12 to the 5, g to the 16 to the 8. But the answer we are going to get here does not correspond to this. The answer we are going to get here does not correspond to this. We are going to do an example to show why it doesn't tally. Right? But that is when we'll look at the trusted setup for multilinear. But for now, let's just focus on the protocol. Are we together? Sure. So, does everybody know how we got 42? How? And the Lagrange basis, right? Okay. So, we've gotten this commitment, right? We send the commitment to the who? To the verifier, right? And after the verifier receives the commitment, the verifier tells us open at right? And how do we open at this? Basically, we evaluate the polynomial at this point. Anyhow the prover wants to evaluate it, it's up to the prover, right? So we can as well still get the Lagrange basis, right? You know, this is still similar to what we do when we do the pair, the pair stuff, right?
I was trying to say how it's linked. It's not a linking.
It's not linking.
Yeah, like that pair stuff.
The pair stuff. Should we? We should, right? Okay. So we have 6, 4, and 0. Let's outline this thing again. So, what is this guy? Right? Right? So, first of all, what do we want to do? We want to partially evaluate that A. Okay. So when we want to partially evaluate at A, what is our pairing going to be?
You are using the Lagrange. Check 0, check 1.
No, anyhow, the prover wants to. The prover knows the polynomial, right? If the prover wants, the prover can generate the Lagrange basis, right? Why we were using the Lagrange basis is because for the commitment, why we use the Lagrange basis for the commitment was because the prover does not know our taus, right? When we get this guy, right? Wait, on. Yeah, it's like. Okay. So, when we get this guy, the prover doesn't know what combination of taus to use, does he? If I give you -8, tell me the tau of A, tau of B, and tau of C I use.
This one was generated by trusted setup.
Yes. So generated in our trusted setup.
What it just did was use this
The dot product with the evaluations of the polynomial to get the commitment. Yes.
So this is like the trusted setup.
Yeah. So this is the trusted setup part that give us these values, right? Actually, not these values, right? Actually, these values. But for now, we're going to be working with this one so that it's clear. You get?
So we're not using we're using powers of okay, so we're not using powers of tau.
Yeah, it's not powers of power. It's the Lagrange basis, encrypted
Using
form of the Lagrange basis. Yeah, not the powers. Why it was the powers in the coefficient case was because of, yeah, and we're working in coefficient form. That's why it was powers of tau.
So if we express the invariant polynomial using evaluation, we can use the same
To commit to it. Yes. But we will not be able to open unless you want to use, I think, is it barycentric? Is it barycentric? Barycentric evaluation. I think barycentric is common too. I've forgotten. But like, if you have the evaluations of a univariate polynomial, you have just the evaluations.
Mm-hmm.
You cannot evaluate that polynomial at any other point.
Aside from those points already,
Aside those points, you have.
yeah.
In order to evaluate the polynomial at any point, you need to interpolate to get the coefficient,
Yeah.
Yes.
Unlike multilinear.
unlike multilinear.
Right.
I think like the barycentric is just like, I don't know.
That's the end goal. It was like we have been draining ourselves.
You know, okay, actually, if you want to think of it like why, right? In the univariate case,
In the multilinear, we are actually still calculating, just that it's not like
it's a straight
it's not
line
straight
in the
line,
multilinear.
that,
Exactly.
linear,
The relationship, the
we
linear
actually
relationship.
still
But in the univariate case, it's not going to be a straight line.
do it.
It's going to be a curve.
Okay, hold on. So multilinear police don't produce curves.
Multilinear
Yeah.
is majorly straight lines.
Why did you say major like?
Because that's how you want to, that's how you can think of it, that it produces a curve. As, okay. When you multiply two, when you multiply two multilinear,
It's no longer
it's no longer multilinear. It's now a multivariate,
Yeah.
right? Basically what we did in
Now
GKR.
non-multilinear.
Sorry, it's now non-multilinear.
No,
thank
no,
you.
it's non-linear.
It's no longer multilinear.
Non-multivariate.
If you are saying non-linear, that means you can need to add multilinear. But if you are saying non-multilinear, because multilinear is a multivariate. When you say non-multilinear, you're just referring to other kind of multivariate. That's
But we get the
Yeah.
point. Guys, the idea is, do we get the point?
The thing is, there's no need to always like say it's non-multilinear. We
There's
already
actually,
know.
there's
Actually,
actually,
once you
there
say
is.
multilinear,
Yeah, it is.
So what?
that's what you're saying. Multivariate,
No, no, the moment, no, when it said that once you multiply, it's no longer multilinear. You understand? We know that it's still multivariate, like it's multivariate, but it's no longer multivariate. So it cannot be univariate.
No, what you said,
Yeah?
This is what you said.
How? When you multiply two
wait.
multilinear.
Now, a multilinear is still univariate with the power of 1.
Of one. That's
So
one.
if I multiply 2 multilinear with the power of 1, I'll get univariate.
You can still get it.
No, I
Like,
think, I think
You can't get the univariate until it's multilinear have more than one value.
univariate can be multilinear. But not
If we have-
cannot be univariate.
if we have 5x times 3x, right? The degree of x is 1. The degree of x is 1. Right. So if we multiply this, we are going to get 15x squared. This is still univariate. You can think of this as two multilinear.
yeah, but it's not by condition.
Yeah.
I'm not saying all multilinear are univariate.
I didn't say that. I said we have 1.
The thing we always like doing complications, come with complications. We are talking about multilinear when it's more than one variable. So this is like when we are trying to like work with like when we are trying to work with the univariate polynomial, right? And we don't want to go through the univariate graph, we want to keep everything still in multilinear. We can do this. But when we are talking about multilinear in the real sense, it's more than one variable. What we are just assuming here is that there's a variable somewhere that has a zero coefficient. That's what we are just
When we are talking of multilinear, when we are talking of is it multilinear you're talking about,
yes,
or
now, like
multivariate?
this 5x we are seeing now, the reason why you're calling it multilinear is because somewhere you just assume that there is a zero coefficient of another variable. Like 5x can also be 5x plus 0y, right? So that is what we are doing here. But in the real sense of multilinear, there has to be more than one variable.
Now against him.
Multilinear,
Multilinear, if you look at the definition of a multilinear polynomial, it's just that all the variables have the power of one.
No. Multilinear polynomials are polynomial with more than one variable. Calm down. Multilinear polynomials are polynomials that have more than one variable. They have the powers of one. You understand? Multivariate is the one that have the powers more than one. Multilinear is a subset of multivariate. So no, him now is saying something else.
No, I'm just saying, like, it's not, okay, based on the definition it gives,
Yeah, you can
not
relate
test
that.
the definition.
No, this
Based on the
is
definition
now.
for now this
No, they said it's not, no, they said,
Which one is not
they said it's a polynomial with variables.
with what? With how many variables?
They didn't say number of variables, that's
No,
it.
that's not it. There's number of variables.
They said more than one.
Yes, there's more than one variable.
And if it was there, fine. If it's not there,
Are you people satisfied now?
They know more than the mentor.
No, I'm learning too. No, serious. I just know multilinear, multivariate. What's my business? You get? But like, these discussions are healthy. They are good because they expose like places that, like, there are some things that I might not have given enough thought, right? So it's discussions like this that will bring it up, right? And make us actually look into it, right? But hope all of us are satisfied. Eh?
Most times when you see like
Yeah, I'm always, yes, which is wrong. I need to work on that. I apologize. I apologize.
So the thing is, Francis is not treating it like that. It is you that is structuring it like that. The moment Francis says that when you multiply two multilinear, you don't get a multilinear anymore. We already know what he's talking about. So it is you now in
what
your
he
head.
says, what he says is that when you multiply two multilinear,
Yes.
you
You get a multivariate. Now, what? So we know. It is you now that need to solve. So see, what's happening to you is called retroactive inhibition. What you already know is countering what you're about to know. Retroactive inhibition. When you already know something and you want to learn a new thing, that thing you know before is affecting the new thing you want to know.
No, but I actually think, like,
contextually, like mathematically, if you multiply, like multiply and multilinear is the subset of multivariate. So if you are saying today I multiply two things and I still get something that is set, it's kind of like I'm looking at it from a mathematical
What you want is for every time he says when you multiply two multilinear, he should say to give you a non-multilinear multivariate.
No, that's not multilinear because when you say non-multilinear, it is multivariate.
Okay, do you know the stress involved in making those pronunciations?
Let's see.
no, don't worry. I would. No, maybe no multilinear will be okay. Yeah, that's not multilinear. But are we okay now? So can we come back? So I get that, like, maybe sometimes the way I say it confuse some people and they get. So that is my duty. So make sure everybody's on the same page, right? So let's see how it goes. Well, I'll try to make sure everybody's on the same page. Okay? Are we okay? Please wait. Okay. Okay, so let's just continue. The idea is that all of us understand what we're talking about, right? I know we're not just supposed to bank on the fact that we understand what we're talking about. We also need to be sure that what we're talking about is actually what we're meant to be talking about. But let me not complicate things. Okay, so we're going to pair, right? We want to partially evaluate at A now. Right? How are we going to pair?
0 and 0.
0, 0, 0. We're going to pair it with what?
1, 0, 0.
1, 0, 0. 0, 0, 1. 0, 1, 0. 0, 1, 1. Right? And what is the equation? What is the interpolate and evaluate equation?
Y2
No, it's y1 plus evaluation constant.
R into Y2
Right? Where R is the point we want to evaluate. Right? And Y2 is basically at 1, right? The evaluation at 1. Y1 is the evaluation at 0. Right? Or should we change it? Should we use 0 and 1? Right? This makes sense. Okay, so for Y0, which is this guy, we're going to have 0 plus, what is that? A? No, that's 6. What is Y1? Right? So that will be 0. Right? So we're collapsing it to 0. How about this one? Is it 0? It's 4, right? Plus 6. 4 minus 4. So that's what? 4. How about this one? 6 into 18.
Sorry, I'm a bit confused.
Okay.
Aru is the random guy that the verifier
Wants to open
wants
up.
to open up.
Yes.
So what's why not and why not?
So why not is the evaluation at 0.
That's why not.
Yes. And Y1 is the evaluation at 1.
Okay, the pairing.
Yes. So these two are constants.
Yeah.
So this one will be Y1.
Okay,
This one will be Y0.
okay.
Makes sense, right? Okay, how about this last one?
Which last one?
This 0, 1, 1 and 1, 1, 1.
Okay, for that one,
Yeah.
y is 0.
Why not? What to be a Y0? Will our Y0 be 0? So this 0, 1, 1, which is this 0, 1, 1.
Yeah.
So
Is the evaluation at the Black Hat and
yes.
Oh, okay, yeah. So that would be 0114 and 1117.
Okay, 1117, right? So that would be plus 6. That would be 7 minus 4, right? Which is 22, right? So we get a new polynomial, which is this, right? We are now going to evaluate this polynomial at b, or partially evaluate it at b, right? B equal to 4, right? So if we partially evaluate it at b equal to 4, what will be the pairings? Yeah, we have a new polynomial. This is our new polynomial.
Now we're going to use for the next.
Yeah, that's what we're going to use for the next. So 0, 0, we're pairing it to what?
1
1, 0.
0 1
Right?
0 plus 15 minus 4 into 18 minus
4 into 18.
0. Yes.
Do we agree with him?
Yes.
Okay, how about this second?
That will be 4 plus 4 into 22 minus 4.
So what is our answer? First one 72. Second one
76.
76. 72 and 76. Right. Okay. Then we evaluate. Oh, yeah. Please, everybody, hope we are following. It's important to follow. Right. That's just 72, right?
Yeah.
We all agree, right? So it's just the evaluation at 0. So we just pick it. We already have it, right? Eh? If C was equal to 2, okay, yes. Yes, we'll go through the normal process. Yeah.
You say evaluation at 0 is equal to 7.
Yes. So we have the value here. We just pick it, right? Okay. Let's still use the interpolator and evaluate. This at 0, right? And this at 1. Evaluation at 0, evaluation at 1. So that will be 72 plus 0 times 76 minus 72, right? So we know this guy goes to 0. Right? Okay. So is our V, this is our V value, right? Is our V value correct?
Yeah.
It's correct, right?
72 is correct.
72, our V.
So was it just to check?
So that's on the way to check it from. Have we gotten the solution?
No, no, not in this solution. On the previous one.
So yes.
Yeah. 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 So well, so that's just what we're going to be doing. When we do it in the evaluation form, we'll confirm it to what we've done in the coefficients form. Makes sense. Okay. So the prover has gotten V now, right?
Yes.
What's the next thing the prover needs to do?
You need to
You
generate
need
the
to
proof.
It needs to generate a proof, right? A proof that V is correct. So this is where
separate the
division
points.
comes in, right? So before that, let's go on a commercial break. No, I was joking. Okay, let's go for the break by one. Is that okay?
Yeah.
So let's just push till one, then go for break.
That 1 hour.
No,
Yesterday you said it was 1 hour.
so that was yesterday.
30 minutes.
15 minutes.
No, today will be like 15. I meant to leave by.
Takes about 10 minutes.
Let's go.
I'll go for the break now.
No, we are pushing to 1.
Yeah.
Yeah.
So that
Say, oh,
Eh?
what about some? Oh,
But let's just continue, right, for now. So we have our V. We need to generate our proof. Prover needs to generate the proof.
That we evaluated.
4, yeah.
What's
0. Can you guys?
I thought it was 5 2.
Okay, so this is where things start getting. This is where things start getting somehow, right? So, guys, pay attention. Okay.
Yeah.
So, in order for the prover to generate the proof, the prover needs to divide.
to what?
To divide, right?
Okay.
You need to divide the polynomial by each of the factors, right? And the idea is that when you divide by a factor, you get a quotient and you get a remainder, right? Okay. So we're working in evaluation form. What does divide even mean? What does it mean to divide in evaluation form? Does anybody want to? Okay, I think like some people made an attempt earlier, right? So let's just, when we divide, we're actually removing a variable, right? We're actually removing a variable. So now I want to think of how, working in evaluation form, how can we remove a variable? What does it mean to remove a variable?
Evaluation. Oh, does not mean the evaluate as 1 over the you want to divide with.
Eh? You made a good attempt. No, like when we divide, we're trying to remove a variable, right? So when we're working in evaluation form, what does it even mean to remove a variable?
It means that you're going to have the evaluation array. And
Yeah,
the
that's
linear
going to
method.
happen.
They're going to what?
The operation comes into place. But then the thing is that the operation, what operation is going to
Like how?
Like
not yeah, like the size, not like the values, like the size of the array will shrink by half. But then finding that
because when we divide, we get a new polynomial, right?
if
In
it's lesser in terms of number of variables.
Wait, oh, how many so we have like, okay, we'll have a set, we should have two polynomials.
the quotient,
The remainder and the quotient.
yeah, we'll have the quotient and the remainder. Okay, not so crazy, sha.
How are we going to form the factors?
Eh?
How are we going to form the factors?
To form the factors.
That's true.
Because we are dividing by the factors.
Factors, yeah.
I think we're giving the factors already.
Like how do you
How do we arrange it like for the moment?
So the factors are like that x, like a minus
Are we
a,
going to like
a minus
also evaluate them
So,
like
since
The
this
factors.
is one variable, I just run it over the
over zero,
Yeah.
over zero,
you say you forgot.
minus six, minus six.
I forgot
Why don't you just divide the evaluation? If you divide it.
to divide all the evaluation.
Yeah, but
So the thing is that the divisors are also in evaluation.
The divisors,
Both the dividend and the divisors, they are all in evaluation.
do they need to be? Wait, okay. If I give you a polynomial and I say evaluate it at a point, right? What do you get?
Evaluate the factors.
yeah,
Yeah,
exactly.
evaluate the question, evaluate.
It should go here. It should go. Should go is not here. Okay. Because this, like the question I just asked, should go ask states. Which day was that? I think the day we're looking at multilinear KZG. Okay, so let's look at this. Right? We have a polynomial. For now, let's work with univariate polynomials. Right?
So we're working in coefficients.
Yeah, coefficient form. Let's go back to coefficient form to understand some things. Then we are now going to come back to evaluation form. Hope that's fine.
Yeah.
So, who should give us a polynomial? Maybe, okay, let's not make it complicated. 3a. So we have 3a, right? And we say evaluate 3a at 5, right? So that will be which is 15, right? Okay. So this is the evaluation of our polynomial, 15. How about if we say can we divide 3a by 5?
How many might leave A by 5?
Cannot do that.
It can't go right.
It's 3 and this is one of the examples for
Okay. Okay, how about like we have 15 now, right? So if we do 3a minus 15, this should be equal to 0. Can we divide this by 5? We can divide it by 5. Okay. Yeah, dividing it by 5. Right? Yeah. What to divide by?
I'm remainder.
We can
If you divide
basically
by three, if you divide by
okay. We can basically factor out 3, right?
yeah, you can divide by three.
A minus 5, right? Right. Okay, so what can we pick from here? That's okay. So we have a polynomial. First of all, we started with a equal to 5, right? When we did a equal to 5, we got a result of 15. That means a is not a factor, right? So in order to get a polynomial that a is a factor, we do 3a minus 15, right? So a or 5 is now a root of this polynomial. We agree, right? Okay, so let's work with this 3a minus 15, which is our polynomial, right? And then a equal to 5, right? Okay. Okay, so a minus 5 is a factor of this, right? It's a factor. So if we divide by a minus 5, so that will be 3, right? 3a minus 15. We agree, right? Okay, now let's look at another thing. Still this a minus 5. You know, when we evaluated 3a at a equal to 5, we got 15, right? Our polynomial is 3a, and we evaluate at a equal to 5, and we got 15, right? So still this 3a, if we divide by a minus 5, which is basically just this, right? What are we going to get? Let's do it. So that will be 3, right? 3 times this is 3a minus 15. If we subtract, does it make any sense? Should we do another example?
Can we go on just
Huh?
can we go over this A minus 5 before
Okay. I'm going to go over it again. Yeah. Well, we have actually been doing it, right? Basically, anytime we subtract, anytime we evaluate the polynomial, I'll get the result and subtract. Yeah, that's basically what we've been doing, right? We are trying to make it a factor, That's why we're doing that subtraction. Right. So let's just look at the example again. Then we are going to do another example. So what was the example? We have a polynomial 3a, right? We want to evaluate this polynomial at a equal to 5, right? How do we do that? We just substitute, right? So 3, the answer is 15. Makes sense?
Yes.
This normal evaluation. So we still have this polynomial 3a, right? And we divide by a. You know, before we evaluated at a equal to 5. Now we divide by a minus 5. So this is 3, right? This is 3a minus 15.
How did you get a minus
A factor. So it's not actually a factor, right? That is why when we divided, we got a remainder. Right? And it's not a root. That is why when we evaluated, we got a remainder or non-zero. Does it make sense? It's not a factor. That's why when we divided, we got a remainder. And it's not a root. That's why when we evaluated, we got a what? A value instead of 0. Does it make sense? Let's do another example.
In this case, I don't to call a minus 5 a factor or what. But I notice like still dividing by 1 over that value for normal numbers. Let's want it to like 2 times 3 now equals to 6. 2 divided by 1 over 3 still gives us 6. That is 1 over 3 like an inverse. So this one, what is it the same?
So this is not actually a factor, right?
Yes, so what do
It's just a polynomial. You get it?
How do we get that?
We're coming. But we'll get to that point. I also want this to be clear first. Right? That when we evaluate and when we divide, we can get the same thing. Let's do another example. Which will give us a polynomial. Huh? 4a. No, let's do something. You can now bring maybe something bigger. 4x squared plus. We are doing univariate for now. We are going to do multilinear. 4x squared plus 2. 4x squared plus 2x plus 1. Okay. So, what should we evaluate it at? Let's evaluate it at 2. So that will be 4. Right? And then, when we evaluated it at 2, we got 21. Let's now use x minus 2 to divide. Right? So that will be, yeah. Let's see if it works. So that will be 4x, right? Right? Minus 2.
Correct.
Right? So does it make sense? So basically we have a way of getting our remainder, right? You know, the prover wants to get two things. He wants to get the quotient and he wants to get the remainder. Right? Because when he gets the remainder, he now divides it again. Yeah, with the other factors. Is it making sense?
I'm trying to think of like what we are going to do with this. So if you evaluate the polynomial, it gives you, when you evaluate the polynomial, it gives you okay, this is usually
Should we do an example with multilinear? Let's do an example, right? Okay. So let's basically do an example with this our polynomial that we've been working with. So this is 3ab plus 4c. Yeah, in coefficient form. Are we together? Right? Where did the verifier I want to open at? For a equal to 6, right? A equal to 6. So let's partially evaluate. Right? Does this guy look familiar? You don't know him? Huh? Is it the quotient? What was that again? 18b plus 4c. Where was that again? So this is it, right? This minus 72 is, yeah. Or let's do the 3ab plus 4c minus 72.
I think I don't know if I'm seeing something, but that means instead of doing the division, when you partial evaluate the polynomial you get after partial evaluating, it's like the remainder, and you can still perform partial evaluation, right? So we don't really need to start looking for a way to do division that way.
Partially. We still need to get the quotient.
Yeah.
We have a way to get the remainder now, right? But if people agree,
Yeah,
like if you partially evaluate,
The next
yes,
linear is, yeah.
you get the remainder. Okay, so did you understand this one?
This one, so you divide it by x minus 2.
No, first of all, this was the polynomial we started with. 4x squared plus 2x plus 1. Right? We wanted to evaluate it at x equal to 2. When we evaluated it at x equal to 2, we got 21. Still that same polynomial, we now say, okay, let's divide by x minus 2, which is x equal to 2, right? But we move 2 over. That'll be x minus 2. So we now divide by x minus 2. Right? So when we divide by x minus 2, we still got 21. So basically the result we got when we evaluated the polynomial at x and when we divided the polynomial by x minus 2 was the same remainder. We now said, okay, let's try it to the multilinear case. We use our polynomial 3ab plus 4c. We say let our a be 6, right? And then we partially evaluated at a. When we partially evaluated at a, we got 18b plus 4c.
So the remainder,
Yes,
we have divided the polynomial by a minus 1.
by a minus 6. Let's just divide it. Or is there any name? Yeah, we've done it before. So if we divide by a minus 6, the remainder we are going to get is the same thing we are going to get when we partially evaluate at a equal to 6. So we have a way of getting our remainder now, right?
Yeah.
We have a way of getting our remainder.
Yes.
Do we all agree?
Yes.
We agree.
Yes.
So now the issue is, okay.
Okay, no, what I want to say is that this one is still coefficient
Yeah.
form.
But you know how to partially evaluate a polynomial and evaluation formula, right? It's still the same thing. Don't worry, we have partially evaluated.
I'm just thinking, it will not look like what we did before. When we started, like our commitment.
The commitment.
Yeah.
Okay, no, the verifier sends
No,
A
I get
equals to
the
6.
details. I get the details.
Yeah.
But what I'm trying to, don't worry. Let's continue to.
No, what I'm saying is that like A is in the clear,
Yeah.
right?
Yes.
The prover knows A.
Yeah,
So and the prover knows the polynomial.
yes.
So the prover just partially evaluates the polynomial at A to get the remainder.
Okay. So, okay, no problem. Continue.
Sure.
Yeah.
Normally, if we're supposed to do this in the long division form, what are we going to use to evaluate the first polynomial? It's supposed to be like a minus 6, right?
Yeah, A minus 6, that's what we use to divide.
That's what we used to divide, right?
Yes. We use it to divide 3ab plus 4c.
We use it to divide 3a plus 4c.
And then,
So I'm asking you, I'm trying to figure out how to get the quotient.
okay, how to get the quotient.
Yeah. So,
So every time we evaluate a particular point, we're going to get the design, we're going to get the remainder, which is equal to like is same as the way we're doing that division.
The division. Is this clear up to this point? Is it clear?
a minus 6 in So that means there's a relationship somewhere from this a minus 6. I don't know, just because if you divide the polynomial by a minus 6, it gives you a quotient. There's something you will do with a minus 6 that will give you back the polynomial.
Is to multiply it to the quotient.
You multiply with the quotient.
Yeah, then you add the remainder.
So can you explain our next issue? We are trying to think how to get the quotient.
The quotient. What was the quotient first? Let's check it.
3B.
Wait, let's
It's 3B.
let's
I think we should do for the
this guy was minus 72, right? So then let's just outline it so that it tallies exactly with what we have before. So that as we are doing, we are confirming. You get? So this will be 18b plus 4c minus 72. Right? 6 times 3, 18 plus 4c minus 72. Part together, right? So this is the remainder. Just partially evaluate at a. You get the remainder. How about the quotient? So for the quotient, okay, let's bring it out. These are 18b plus 4c minus 72. So the quotient is 3b. Right? 3b. How do we want to get 3b? Actually, the funny thing is that it's quite straightforward, but it's not intuitive. In a sense that when we divide, we're taking away all the places a is, right? So these are polynomial 3. Okay. These are polynomial 3ab plus 4c minus 72. If we partially evaluate this polynomial at a equal to 1, what are we going to get? We are going to get 3b plus 4c minus 72. Right? How about if we partially evaluate this polynomial at a equal to 0? We are going to get 4c minus 72. Have we seen the answer?
Do one again.
Oh.
Eh?
Do for
Wait,
do for
if
C.
you, oh,
No, do for C.
wait, if you subtract these two, you get 3B.
Exactly.
Wow.
So if we subtract the evaluation of the polynomial
That's
at a equal to 1 minus the evaluation of the polynomial at a equal to 0, we are going to get our quotient.
one. Wow.
That one for Jesus.
Wait, I don't understand. A equal to 0 gives you that. From when?
This is a polynomial.
A equal to 0 gives.
If a equal to 0, this goes off, right? So we are left with 4c minus 72.
Okay.
Yeah. So if we subtract 3b plus 4c minus 72. We're subtracting 4c. Right? Set theory. It's basically to explain this. Now, I've not talked about it, but why does this work? You think you know? Okay. Sorry, let me just cancel this time, right? So we have 3b.
Now we're working in binary, right? So A is supposed to be either 1 or 0. So you find the evaluation of A as 1 and find the evaluation of A as 0. You're supposed to, so that's remainder, right?
Think about it with respect to set. But we're coming. We're going to talk. I want, let this one cement first.
But why does it give us a
Yeah, that's the question. That's $1 billion question.
Why does evaluating is polymer and subtracting it from like evaluation of polymer to give it a quotient? Why?
But
Wait. So this one is f of 1 and f of 0 are set. F of 1 is set of monomials that contain A as one of them, and f of 0 don't contain A. So it's like, this instead is this subtraction of not look at isn't no not look at this subtraction of two sets. There's that subtraction.
I like where it's going.
Before we enter that set, before we
Okay, but let this make sense first. Once this makes sense, then we're going to now talk about the set stuff. Okay, so this was just one example. What if this doesn't hold?
You already said it. Try on that one.
I already said.
Yes.
I not said it, you know. Okay, so let's try another example, right?
You don't have big beginning.
Yeah.
Oh, it's not by 2.
Yes. Yes, it's recorded. It's recorded. Yes, it's recorded. Huh? Okay. Let's just calm down. We're still going to do the sets. So the people should just bear with us. Let's just run through till 2. Right. Please. Okay. Eh? What is that? Okay. Okay, but this was just one example. So basically we found the quotient and we found the remainder. This was supposed to be like a 2 hours class. Finding the quotient and remainder, but we're done, right? Okay, so let's just do another example, right? We have this as a remainder, right? Let's try and see if we can actually use it, if we can get the quotient and the remainder with respect to b. What was our quotient with respect to b? 18, right? What was our remainder with respect to b? 4c. It was 4c, right? So let's see if it works. It's 18b plus 4c minus 72. 18b plus 4c minus 72. And what is our b? Okay, b was 4, right? So our b is 4. So if we want to get our remainder, what do we do?
The partial evaluation.
4. So that's 18 4 plus 4c minus 72. So what is this? What's 18 times 4? 72. Does it work? It works, right? How about our quotient? We've gotten our remainder. How about our quotient? Which which variable are we evaluating as 0 and 1? So at b equal to 0, we have right, which is 4c minus 72. Right? Which is 18 minus 72 plus 4c. So what's the answer? That's 18 minus 72. That's minus is that 50?
18 minus comes to plus.
No. It's 18 minus 72, right?
Okay. Oh, sorry.
Minus 54 plus 4c. Interesting. So if we subtract, right, b evaluated at 1, that's minus 54 plus 4c minus 4c plus 72. So this goes off, right? Eh? No, this is the quotient. There was no. It was just. Yeah. Just evaluate at 0 and 1. Yes, yes. Sorry, I'm coming. Let me just show. It was actually 18.
Okay, because the up that was 3B.
Yes. Is this one that was the up that was 3B, which we got. Does it make sense?
Yeah.
So, why?
Second check.
Funny enough, we didn't.
Second check.
Like, eh?
Second check. Okay. F of 1, right? Okay. B being 1 or B being 0, right? So F of 1, like I said before, gives us the set, the polynomial that has B in it because we are setting it to 1.
Let's use Venn diagram.
Okay.
But I want to be sure that this
It's okay.
we understand, right? So let's look at the Venn diagram. This is A, this is B, this is C. Right? Here is what?
Combination of two.
Huh? Yeah. So you can think of it as ABC, right? What is this other place? This AB. This is this entire one is, A is also here, A is also here, right? So this A, AC, AB. But this place, that's just A. This place in green, right? Inside. Instead of, okay. So I need to make it bigger.
More like wide.
Like we should draw the
Wide
circles
out.
first.
Wide out.
Okay, wider.
Yes, wide
Maybe we
out.
should draw the circles first before you draw
Okay, before putting this.
Don't the circle. Don't show the circle.
I'm not a good artist, so you guys will bear with me. So this A, B, C. Let me write it inside.
So, I don't know. The entire circle is right. Yeah. But why are we not calling only AA?
Here?
Yeah, it's supposed to be A
Oh.
intersection.
Oh, okay.
B union. C
Oh.
Like that, you.
The union stuff.
Yeah.
Well,
Or you can just
but if people understand, like, this one is just, yeah.
Just put it, you can just put like prime so that it's different. You can just put it.
Is it okay? This is better, right? And then this is the universal. Is that how to write it? That's not like this. Okay, so if we want to take out A, right? How can we go about it? A from everything.
Just like the pure A, right? A.
Okay. Basically, like, if we evaluate A, this is a set, right? If we evaluate A at 0, that means this entire place will go to 0, right? This guy will go off, right? This guy will go off, this guy will go off, this guy, this guy, this guy, this guy. They will all go off. What are we going to get? Well, let me just draw a small representation. We are going to get something like this. I don't know how to draw. So this is B, right? And then BC is something like this. This is BC. And then C. Okay. I think I've gotten it. Glory to God. So this is C. Right? How about when A is equal to 1?
Comes back.
This guy comes back, right? This guy comes back. Right? So, what is the idea? So if we subtract this guy from this guy, from everything, if we subtract this from everything, what are we going to get? We are going to get the A circle, right? We are going to get this A circle.
If we subtract, we're going to get just the car of that A. That's almost like another, maybe A prime.
So we are removing these other guys. Yes, green and good. Right? So we are removing it. So what remains is actually this guy. Does it make sense? Okay. So that's basically like when A is equal to 1, right? That's when A is equal to 1. So when A is equal to 1 and the others are equal to 0. So A is equal to 1, right? The others are equal to 0. So that would, yeah, that is a small A. So this is like A equal to 1, but let's say B equal to 1 too, right? That is when here will be active. This A equal to 1, B equal to 1, C equal to 1. That's when here will be active. This A equal to 1 and C equal to 1. That's when this place will be active. Right? So if we have like A equal to 1, C equal to 1, B equal to 0, that will basically take off B is equal to 0, right? So this will go off. Right? This will go off. So what will be left with is, I don't know if you guys are even seeing. So what will be left with will be this guy. Where A equal to 1 and C equal to. Where A equal to 1 and C equal to 1. Right? but b is equal to 0. So that's just basically, you can just think of that as like what is going on. So when we say a equal to 1, we are basically talking about like this guy as a whole. And when we subtract it with when a is equal to 0, when a is equal to 0, this guy goes off, this guy goes off, this guy goes off. So we are just left with when a is equal to 0.
You can pair it up with me. What the
You know it's equal to
Yeah,
zero, all
exactly.
of these things.
it also equal to
When a is equal to 0,
If you go, let this you
yeah, this guy will
All
go,
of them.
this guy will go, this guy will go, right? So when we subtract when a is equal to 1 from when a is equal to 0, right? Right. Hope I'm not making things complicated. Okay. Right. You see?
So you
Oh.
change the date.
But we get the fact that when a is equal to 0, this is what we get,
Yeah.
right? Because all these other places basically turned off, right? Then when a is equal to 1, this other place, like this place is packed, right? So when a is equal to 1, and then we're also like considering the others, that's basically get everything, right? So when we subtract this from everything, we just get this part. Where a is equal to 1. Like, I know it may not make total sense now. It may not make total sense now. But why I brought this up is just so that we can try to get an intuition of what is actually going on when we do the f of 1 minus f of 0. Okay, but the major go home here is this, right? That we know how to get our quotient and that we know how to get our remainder. How do we get the quotient?
Value at 1 and 2 and subtract.
Evaluate at 1 and evaluate at 0 and you subtract it. How do we get our remainder? Partially evaluating at the value for a, right? So basically with that, I think with that we can have our multilinear KZG, right? Yeah, except for the shortest setup.
Is it good?
So the shortest setup we have not looked into it yet. So we're not done, right? We're still on the evaluation form. We just looked into the coefficient form to see how it's actually done.
So that means that actually
Wait, I must get the date.
Essentially, to get this, we know that continuation of that input.
Yeah, I people know how to evaluate multilinear polynomial evaluation form, right? So it's basically still that you interpolate and evaluate function you use. So
I still don't get why the quotient is equal to losing and one subtracting from the other losing and zero.
so how do I explain this? So when you evaluate at 1, okay, say we have a set, we have this set.
I think you use
Okay, 2. Okay. So we have this set, right? This A and B, right? Yeah, that's two variable, a two variable polynomial, right? So here is AB. That's what you said, right? Okay, good. So if we partially evaluate this at A equal to 1 and B is equal to 0, right? B is equal to 0, this will go off. A is equal to 1. That's basically this portion here. Right? Let's say A is equal to 1, B is equal to 0. Right? So B goes off because there's no B.
So, from what you're saying, I think if B is 0, the shape of A should still be whole, completely intact.
Yeah, it will be whole. Well, I'm just trying to draw out like what B is equal to 0 is basically like B not being there. You get
Well, as we're like
curving it.
Curving it, so it was
Okay.
like, I don't know, maybe it's a part of it, none of that.
Okay,
But then
no.
we'll also not have AB, right?
Yeah, AB will not be there.
Yeah.
No, like,
You're just removing B now, so A will still be
but anywhere A is combined with B, you know, since B is going off, B is going to take it along.
Just say it's in
And
that
B will
polynomial.
just go leave the
If it's in that
leave
polynomial,
the house.
if it's in that polynomial, they are always going to like intersect. So even if B is 0, it doesn't matter if you take it out. So that equation will still be there, and you have
B
to
just leaves.
evaluate it. Like it doesn't mean that B totally
That
goes away and the A is
part
A will still not be good because you are
Yeah.
still in polynomial and you're evaluating that to be 0. So let's say there's now AB. When A is 0, it multiplies the counterpart and cuts it eventually. I think it's good.
Yeah. Okay. So
But B does actually take everything combined.
eh?
Like B takes anything combined with
Yeah, anything combined with it. It takes it away when it's 0. Yeah. We're trying to get the quotient.
Okay, using this.
Yes.
Okay, I don't see the intuition
Behind, yes. Why A evaluated at 1 minus
So if
A
A
evaluated at 0.
Did we get did we get the quotient for that equation, that last equation? What was the quotient for A? Like when we divide by A, what was it?
Yeah, when we divided by 8, it was 3B. That was the quotient.
3B. Okay.
So like, is it like values are going to represent complete Yeah, because look as if you are doing it backwards, like structuring the problem.
How? It's a set now.
Okay. Like is it correctly, is it these values that are up that need to represent you are trying to understand
Okay, no. I was just thinking about it abstractly.
the abstract?
What would you
Structuring the set one by one, just so that
what would you mean in evaluation?
In evaluation form, the remainder, it will be a new polynomial, evaluations of that polynomial. Yeah. Yeah, exactly what the partial evaluate returns.
I said exactly. I'm talking about the quotient now.
The quotient, no, it will still be, yeah, it will still be a polynomial. You're subtracting two polynomials,
Okay.
so you're going to still get the polynomial.
Yeah, sure. Like I'm like, so it will be a polynomial in two variables for evaluation.
You know, it's element-wise subtraction you're doing, right?
Yeah.
So it's still going to be like this thing, but it's still going to be based on the array, right? It's still the number of elements in the array, but it will cancel out,
Yeah.
right?
That's what I'm saying.
Element-wise subtraction, so some values will be zero.
Yes. So that means at the end of the day, our polynomial should be lesser.
The size
Yeah, the size should be lesser.
should be lesser.
Yeah.
Well, it will be lesser, but in order to evaluate it at tau,
Okay. Okay.
yeah, in order to evaluate it at tau, you still need to do that dot product. You get. So and in order to do a dot product, the both of them needs to be of the same length. Yeah.
I'm trying to remember where we did how multiplication. Okay,
That was in the
did we
commitment. Yeah, we did it.
Okay, here, that was it. This one was not the original equation. That's the original equation.
Yes, this is the original equation.
Yeah, I'm talking about the quotient equation kind of.
The quotient.
You have to evaluate the quotient equation out. Yeah. So yeah, this one remains. I was not asking about this one. I was like the quotient equations, if we have to evaluate it at tau. Right? So if it will be tau A, right? If we divide by x minus a minus x minus a now, for instance, we will evaluate the quotient at tau A, right?
Yeah, we evaluate the quotient at
Tau A.
if we divide by x minus a, the quotient we are going to get, you know, a is going up,
Yes.
so it will most likely be a quotient in say maybe ABC, right?
A is going up, so right,
Yeah,
is-
but like it can still be okay since it's multilinear. If it was multivariate, what is on top can be 3a, right? Like you can have a case where we have 3a and a minus 6,
Okay, yeah.
right?
Yeah.
But since we're working with multilinear polynomials, this shouldn't be, because if we do this multiplication, it's going to give us a non-multilinear,
Okay.
right? So this will be a polynomial in, let's say, BC.
So that was why I was saying that the quotient should be reduced.
Yeah.
The length should, since it's really going to be C, that was what I was going for. But just for general motivate, should make sense.
Yeah. So I think let's quickly just look at that let's quickly just finish up what we were doing, right? We've understood how to get the coefficients, right? Sorry, the quotients, and how to get the remainder, right? So let's do it by hand now. Let's just continue the protocol. Where did we stop before we? Okay, so the prover needs to generate a proof. What was the polynomial again? That was 3ab plus 4c minus 72. Okay, and let me just outline everything again. Our tau A, tau B, tau C, and also our ABC. Right? Is this what I was supposed to be copying? This was not it, right? It's the evaluation form. We want to generate the proof polynomials in evaluation form. Is it making sense? Okay. So in order to generate the proof polynomials, we are going to partially evaluate this guy at A to get our remainder, right? And then we are going to partially evaluate it at 1. No, we are talking about A for now, to get the quotient and the remainder. So for A, right? Are we together?
Yeah.
We're going to partially evaluate this guy at partial eval at A equal to 6, right? Okay. So what's our normal pairing? Right? We know our y0 plus r y1 minus y0. So what is that going to be? Have we not done this before? I thought that was for the...
That was what I was asking you before. I hope they will not be the same. Down.
Okay.
Yeah, that's it.
Where? Okay. Okay. Yeah. So we have 0, 4, 18, 22, right? As our remainder. Right? We We have 0, 4, 18, 22 as our remainder.
Then we now get the quotient.
So we now need to get the quotient.
So this remainder now is going to be the input for the next round.
Yeah, for the next round. But do we agree that 0, 4, 18, 22 is actually the remainder? What was the remainder in coefficient form?
18B plus 4C.
Minus 72. 18b plus 4c minus 72. So let's just quickly check. So that's 18b plus 4c minus 72. And is 0, 0. So that's is this it?
Are you sure it's not 18B plus 4C?
So it's 18b plus 4c, right?
Yeah, that was what it makes sense. So the factors are irreconcilable.
Yeah.
Please confirm.
I know, like, you guys are tired, right? Yeah, yeah. See it. It's recording. You don't need to fear. Okay, so actually that was on the original polynomial. That was where we did this one in order to get the partial the evaluation at the point the verifier said we should open at.
Yeah.
But you know, when we want to now get the proof, we need to now subtract 72, right? So painfully we'll need to do this again, right?
Ah.
You understand?
Yeah.
Okay, so let's see how far we can go. Okay, so this is not even the polynomial in evaluation form again. This is going to change basically. So that'll be okay.
I feel we don't have to go whatever you get, your final answer.
We just subtract 72, right?
And that is
Yeah,
So
actually.
the first one will be minus 72. You can just roll it over and copy it or paste it down. Yeah.
Okay. So this will be minus 72. This will be minus 68, minus 72, minus 68, minus 72. This will be
Are you doing it again? Are you doing it again?
yeah, we're doing it again. You know, the only difference is the minus 72 now.
Okay, that one was wrong.
So I think for the case of those that will be watching the video that are not in class, let's say the video online, it will actually be cool to bring this value here, do minus 72 on all of them, then the equal sign and just write everything, because like this now someone will think like
Okay.
out of this
Yeah, that's true.
Oh.
Yeah. Very
So you can do minus 72 on all of them, then report to this other guy.
Yeah.
Okay.
Because
So it's like minus 72 on all of them, then
Okay.
report to minus 72 minus 8.
then report to or you could do
Right.
Yeah.
This is similar.
yeah, 69. Minus 65.
Interesting. All negative. Okay, so this is our polynomial, right? And then we want to divide. So how are we going to do? Let's get the remainder first, and then we get the quotient. So that will be 0, 0, 0, 1, 1, 0, 1, 1. What's our formula? Y0 plus R, Y1 minus Y0. Right? So that is,
It's 3 zeros. Yeah. 0, 0.
yeah, but you know what? I'm going to pair it. So I'm just,
Oh, okay.
yeah. Eh? Yeah, no longer it. Or should I still?
This is like continuation of what we are doing before.
Yes.
Go to the question leaders for all the three.
Eh?
Go to the question that leaders individually. Isn't that a method that you said before? Without the English.
Yes. So that was the coefficient form. That was the coefficient form.
But that was still coefficient form. No, that was already the evaluation.
You know, we had to resort to the coefficient form to understand some concepts.
Okay.
But we did something similar. That was when the verifier told the prover, okay, open the polynomial at 6, 4, and 0. But what we did it on was on 3ab plus 4c. The minus 72 was not there. When we now open the polynomial, the 3ab plus 4c polynomial at 640, we got 72. Right?
Yeah.
So that 72 now is what we now subtracted to get f of abc minus v. This is f of abc.
Going to
201.
Yeah, I think like
the physical.
no, like this. Eh? Yeah, I get it. So let's just I know like all of us understand it already.
Sort of.
Right. Is there any okay, so while we're waiting for the light, is there any point in the flow that doesn't make sense yet? I know it will eventually make sense. I trust you guys. So it will eventually make sense. So, but is there any point in the flow that doesn't make sense yet? Huh? We all understand the flow, right? We know what's supposed to go on. We know how to get our remainder. We know how to get our quotient. Basically, that's it, right? So I think the major thing now may be how to commit to the quotient. That may now be like the major next thing, right? Yeah, trust Linux. Yeah, it's recording. Okay, so this is going to be minus 72 plus what's our R? 6, right? Minus 72 minus, right? So this minus 68 interesting. I expect to be minus 68 again. Why is it so weird? Right? This one's 0, 1. Right? Seems everybody have given up.
Continue.
Yeah, it's minus 68. Sorry, yeah. Is it not 65? Sorry. No. Okay. Hope I didn't make that mistake any other place. Okay. So this guy is basically minus 72 minus 68. So this is as 318 minus 72 plus 18. That's minus 54. And is it 54? Ah. Yeah. Minus 50. So this is our new polynomial, right? This is our remainder polynomial. Right? Let's just quickly confirm. What is the polynomial supposed to be? 18b minus 4c minus 72, right?
Yeah.
Are we sure? So 18b plus 4c minus 72. It's minus 68. This is minus 54, right? It's 18 minus 72. And then 22 plus 22 minus 72. So it's checks, right?
Yeah.
So we're just going to do this for, yeah, we need to get the quotient. We've gotten the remainder. Let's get the quotient. What is the quotient basically? We split this guy into two, right? we split him into two now,
Yeah.
right? Evaluation as 1 and evaluation as 0. Right? We're actually subtracting, right? So this will be this will be 0, right? This will be 0, right? This will be minus, and this will be minus. Right? Huh? You see? This is,
Quotient.
yeah, this is our quotient polynomial.
So this is equivalent to this thing, how many B?
3b.
3B.
3b. Yes.
That's where it's fine.
Eh? Yeah, this. Sorry. Actually.
Well, the sign is 65.
So this is actually, yeah. So this is the evaluation at 1, and this is the evaluation at 0 of this polynomial.
Sorry, why did we slow down? Why did we change it to use remove the minus in front?
Okay, no, because I just splitted it. So what I was doing initially was evaluation at 0 minus evaluation at 1. But it's actually meant to be evaluation at 1 minus evaluation at 0. Right? So this is actually the evaluation at 1. Right? This is the evaluation at 0.
Sorry, from where it's
It's with respect to A. I'm working with respect to A.
But they all have minus in front of them now. So why are we removing a minus from the other side?
Right. Wait, let's just.
When you switch F0 now, you switch it already, so that where you take
So this was minus, right? Okay, this guy is minus values, right? This minus 68.
That one is still F of 0.
F of 0.
When you put F of 1,
Because
it's
you
actually F
switched
of
it.
0.
Look at
You only
Look
switch
at the
because
array.
of the minus.
Okay,
The
okay.
values that under F of 1 are actually values for F
F
of
of
0.
0 ends with 68, F of 1 ends with
Yeah.
65.
Let me switch it back so that especially for those that will be watching the videos, right?
that F of 0 is
It's F of 1. Yeah. right? So that's 72, 68, 69, 65. Then minus 72, 68, 72, 68. So but minus minus will become plus, right? Okay. So this is 0, 0, 3, 3, which is still 3b, right? So 3b, 0, 0, right? Right? So that would be 0, 0, right? Yeah, there's a C. So that's why we said like Q of A with respect to B, C. Right? So this is B and this is C. So when it's 1 is
It's supposed to be that polynomial was supposed to evaluate as b equals 0 and b equals 1.
yeah, this is the
So this
polynomial.
equation. Yeah, you want to like confirm, right? You're supposed to put b equals 1 inside that polynomial, eating b equals x. And also put b equals 0, then subtract it to see if you get that, right?
No, like the quotient is 3b. When we did it in the coefficient form, it's 3b. So I wanted to confirm.
Okay.
Yeah, so 3b over the Boolean hypercube of BC is this, right? And when we evaluate it, these are the values we will get. You get. This one is the one we got when we did f of 1 minus f of 0, right?
Yeah.
Hope
Okay,
it
yes.
makes sense now, right? Okay. So with this, basically we just continue the process, right? We just continue the process. We partially evaluate, get the remainder. This is our remainder, right? This is what we use to go further. Going further, we partially evaluate it at b is equal to 4 to get the new remainder, right? And then we do the subtraction thing again to get the quotient, right? So I know this is something of you can do, like, and I'm sure it makes sense already. And I can see a lot of you are tired. Me too, I'm tired. Eh? I'm not a robot. Okay, so I think with that we've come to the end of today. So you guys should. Whose Multilinear KZG am I expecting to see tomorrow? Eh? The trusted setup. For now, people should just implement. Yeah, that's implement without the trusted setup. Right. I write your tests. For the multilinear case, that is when we have. No, you're still going to generate the trusted setup, right? But it will be just one person that can contribute for now till we have figured that stuff out. Right? Yeah, it's still good.
You said everything we learned today encapsulates like the Multilinear KZG. So what's
Like basically, you guys understand Multilinear KZG. You do, right? Technically. So what is multilinear KZG? You commit to the polynomial, right? You know how to get the Lagrange basis, right? And you know how to do the dot product in order to get the encrypted evaluation. You know how to encrypt, right? You get the Lagrange basis, and then you just raise the generator to the Lagrange basis. Yeah, you can get it from. Yeah. So I'll say you guys should use BLS 12381. Like that's what you guys will use. Yes, ACOX. Yeah, you'll be able to get a generator. So you'll be working with pairings. You know, before you've been doing F, I constrain it to be a prime field. But now what is going to be will be P, and you constrain it to be pairing. Yes. So, is it making sense?
Like in the implementation.
Yeah, in the implementation. You know, normally you have F, prime field. Right? Let's say if this is your function W, right? Right? So right? But now it will no more be fields. It will be
What does it mean?
Pairing.
yes, pairing. So the pairing, yes, you get it from our course. On this pairing, you can call G1. You can call G2. Huh? It will give you, like, you can call G1 generator, and it will give you the generator of G1. You can call G2 generator, it will give you the generator of G2. Right? Yes, it returns a point. XY coordinates. Right? So once you have this generator and you've gotten your Lagrange basis, all you need to do is the generator. Let's say if your generator was, so it will be the generator times the Lagrange basis, right? So element wise, we're just putting all of them into the G1 group. I believe all of you are senior devs now. That's why I'm going this way. Eh? So let me see what people can use this information to do first. Okay.
You know you're doing like a dot pairing, a dot multiplication between the Lagrange basis with this G generator and you're doing that what? Okay. And you're doing that against evaluation points. I just go to evaluation points to G or will that work?
For which of the evaluation points?
The major evaluation point, that's what I do with dot product right now. The dot multiplication of
No, first of all, to get your powers of tau, you pick random values for tau, right? Let's say tau A, tau B, tau C to the tau n, right? And based on this, you generate the Lagrange basis, which will be 1 minus tau A, 1 minus tau B, blah, blah, blah. When you do all this, you get an array of field elements, right? Yeah. So this array of field elements, you're going to multiply each of them with the generator to now get an array of G1 elements, right? Right. Then, when it's now time to evaluate these points, you're now going to multiply them with the corresponding evaluations of the polynomial. These points.
yeah, that's what I'm trying to make confirm.
Right.
What I'm trying to confirm now is that these generators, they are pairings.
Yeah, there are points, x comma y points.
Can you multiply this x comma y against evaluation points that are just
That are scalars.
Yeah.
Yes. Yes. You get, that this is what it technically means, right? Does this make sense? Like, I know I'm writing rubbish, but it makes sense, right? Yeah, I know you guys. I trust all of you. Okay, so
So the generator can allow subtraction to
the generator, like if you have 2 points,
you want to subtract.
yeah, you can basically you negate one, right? Then you add.
Okay. Then how do we do target?
The target group. Okay. So, like the multiplication, right? There's actually a function, a pairings function.
Okay.
So you just call pairings. I don't know if there's an S or not, but there's a function pairing, right? Where you pass in G1, a point in G1 and a point in G2. Yeah.
Then to produce GT.
Yeah, to produce a point in G2.
How do we know the generator is using GT?
In GT, you need to look through their code.
Eh?
I think like everything should be in the code, but you don't need to know technically. But if you want to know,
Okay.
yes.
Since you just need to compare.
yeah. But I think in their documentation, they put it. So, yeah. I think in their documentation they put it. You can also try to print out the GT element and see how, like compare the size to the G1, G2 element. There is something you guys can give a shot. Just give it a shot, give it a try. You can, right? Eh? I know you guys are expecting design session, right? But this is our design session. Eh? Implement multilinear KZG. Is it a pre-commitment? It's actually a commitment.
What do you mean to commitment on commitment?
Pre-commitment just came to my head. Like,
No, I've seen pre-commitment. Right? There's
what? What is it? No, it's using KZG, not multilinear KZG. Yeah, are univariate.
Okay, once it's variant, you just call it KZG.
Sorry, you wanted to ask?
So yeah, like pre-commitment. And there's another word that is coming to my head. Stick with something. Like when you want to hash a value, there's the input. There's the word they call it.
Pre-image.
Yes, pre-image.
Okay.
So pre-image, pre-commitment.
No, there are different things.
The pyramid is the same as mass.
Yeah.
The pyramid is the same.
Yeah, it's the same thing. So before you map an element to another element, yes, the X
X
value.
value, yeah.
So what's pre-commitment? What is commitment?
Pre-commitment, I don't know if there's anything like that. There may be, you get, but pre-commitment is English now. Before commitment. So maybe anything you do before committing to a value.
No, but wait, consecutively your elements is pre-commitment or pre-commitment.
Okay, no, I was like, multilinear is it's a commitment now.
Yeah.
What else does it?
Yeah. But when you were saying deep commitment or commitment.
No, I wasn't saying it. So I was being, what do they call it? English,
So what
sarcastic.
exactly are we doing?
Thank you. Eh?
What exactly is the assignment?
Implement multilinear KZG.
Yeah, I heard the statement. It's just what exactly are we expected to take in and
I don't know how to answer the question again. Like, implement multilinear KZG.
yeah,
Is it difficult?
How many times? Everything is scattered.
Everything is scattered.
Yeah, like
Is everything actually scattered?
not here. Yet.
Okay.
So it's just like the central points to bring
But
them all
you understand the flow of the protocol, right?
Yes. Well, I've seen also where we are using that the Lagrange system. The Lagrange basis that we generated. And I think we've not used this basic equation yet.
Serious.
Oh, we use it to get the initial commitment. Yeah, to comply with that distinction. To get the initial commitment. Is that your only work?
I don't know how I want to say it again. Like, the work is
what
to
do you
implement multilinear KZG.
Yeah.
That's the work. Implement multilinear KZG. Just start implementing. It will make sense. Like, in as much as you understand the flow of the protocol, right? Start implementing, like everything will come. Yeah, already it's about to come.
When is done,